Hello there and welcome to Physics with William, where curiosity settles in for the evening and science is allowed to take its time. Tonight we're easing into a question that sounds almost simple at first, and then very quickly becomes one of the most extreme questions physics can ask. How much pressure can matter take? Not how much pressure can a bridge support, or how much pressure a submarine hull can survive, though those are certainly dramatic enough. I mean matter itself. The actual substance of the universe, the stuff in rocks and rain and bone and steel and stars. How hard can reality be squeezed before it reaches a point beyond which our ordinary ideas stop being useful? It is the sort of question that begins with something familiar. A thumb pressing into a cushion, a boot sinking into wet ground, a hand gripping the lid of a stubborn jar. Pressure is one of those quiet physical facts that accompanies us all day without demanding much attention. You feel it when you lean back into a chair. You feel it when water presses against your ears in a swimming pool. You feel it when a backpack strap digs into your shoulder with far more enthusiasm than you would like. Most of the time, pressure is a nuisance, a convenience, or a simple engineering concern. It helps tires grip roads, keeps airplanes aloft in a strange indirect way, pushes water through pipes, and occasionally reminds us that one more suitcase probably was not a wise decision. But when physics looks at pressure closely, it becomes far more than just force in a cramped space. Pressure becomes a kind of test, a stress, a challenge issued to matter itself. Hold together if you can, resist if you must, rearrange if you have no other choice, and under ordinary conditions matter performs quite well. A table survives the weight of dinner plates, a wall holds up a roof, a mountain sits there for millions of years looking very confident about the whole arrangement. Yet nature is not content with ordinary conditions. Nature likes deep oceans, collapsing stars, planetary cores, shock waves, explosions, and regions of the cosmos where matter is squeezed so brutally that the word compressed starts to sound almost polite. Before we drift any deeper into that, I would love to know where in the world you are listening from tonight and what sort of hour has found you. Is it late where you are? Is it one of those quiet evenings where the house has finally settled and all the louder thoughts have begun to lose interest? Or are you listening in the early morning, somewhere between the last traces of sleep and the first demands of the day? It feels rather fitting, really, to wonder about pressure while each of us sits in our own small pocket of circumstance, under our own weather, our own gravity, our own day. And if you find this soothing or interesting or simply a decent companion while your mind starts to slow down, I would be very grateful if you gave the video a like and perhaps subscribed. It helps this calm little corner of science find more people who might enjoy taking the long way around a difficult question. I always think there is something very nice about treating the universe this way, not as a list of facts to rush through, but as a place we can sit with for a while. Now, when you first hear the phrase Planck pressure, it may sound a bit severe, a bit official, like the sort of thing that comes with a clipboard and no sense of humour. But behind the term is a wonderfully direct idea. If there is some ultimate scale at which our present understanding of physics can no longer be trusted, then perhaps there is also an ultimate scale for pressure. A pressure so enormous that it does not merely crush objects or deform atoms, but drives us to the edge of what our theories can sensibly describe. It is the kind of limit that does not concern the survival of a building or a machine. It concerns the survival of our explanations. That is what makes this topic so interesting. It is not just about violence, collapse, or smashing things, flatter than they were a moment ago. It is about the relationship between matter and resistance, about the fact that the universe permits squeezing, but not without consequence. Push on matter and it pushes back. Press hard enough and its internal structure begins to matter. Press harder and the rules change. Harder still, and even the revised rules start to look uncomfortably incomplete. If you think about it, pressure is really the universe insisting that space is not free, or at least not easily surrendered. Every object takes up room, and the moment you try to reduce that room, something answers. Sometimes it is the stiffness of a material, sometimes it is heat, sometimes it is electrical repulsion between particles, sometimes it is one of the stranger quantum effects that sound made up until you realize entire stars rely on them. Matter, in other words, does not simply sit there waiting to be compressed like an obedient cushion. It negotiates, it resists, it changes strategy. A simple example will do nicely here. Take a sponge. You can squeeze it with 2 fingers and make it smaller without much drama. The reason is not that the sponge enjoys the experience, but that a sponge contains a great deal of empty space in its structure. Air escapes. The material folds in on itself. The object becomes denser, all very manageable. Now imagine doing the same thing to a brick. Quite a different conversation. The brick has less room to give. Its particles are packed in a sturdier arrangement. It resists more strongly. Squeeze hard enough and instead of neatly shrinking, it cracks. Already we can see something important. Not all matter takes pressure in the same way. Some materials compress easily, others barely compress at all. Some bend, some fracture, some heat up, some change phase. A gas in a cylinder can be compressed significantly. A liquid, much less so. A solid might hold firm for a while and then suddenly fail in a way that is loud, expensive, and deeply inconvenient for whoever was standing nearby. And yet, all of this everyday material behavior is only the beginning. Because the deeper question is not whether familiar objects can survive pressure, but what pressure does when there are no easy spaces left to collapse, no simple structural rearrangements remaining, no comfortable mechanical tricks to absorb the burden. What happens when matter is pushed beyond the range of ordinary chemistry, beyond familiar solids and liquids, beyond the scale where you can still talk sensibly about a substance keeping its shape? At that point, the story begins to leave the world of furniture and engineering and enter the world of planetary interiors and dead stars. Deep inside planets, matter exists under pressures so vast that rocks no longer behave like the rocks we know at the surface. Down there, materials are forced into denser forms, their crystal structures change, their properties shift. A mineral that seems perfectly stable in your hand might adopt an entirely different arrangement when buried far enough beneath thousands of kilometers of overlying matter. The pressure does not ask politely. It simply keeps increasing with depth, because every layer has the weight of all the layers above it pushing down. This really is one of the great cosmic habits. Gravity creates pressure. Gather enough mass into one place, and gravity squeezes the interior. A modest world gives you a modest squeeze. A larger world offers considerably more. A star, having gathered an absurd amount of mass and then had the audacity to ignite, becomes a pressure factory on a scale that makes the core of a planet seem almost relaxed. Inside stars, pressure is not just present, it is essential. Without inward gravity and outward pressure in a delicate contest, stars would not shine at all. They would either drift apart or collapse into a very different sort of object. What is lovely, in a stern and slightly intimidating way, is that this contest between gravity and pressure is one of the main themes of the universe. A star lives because pressure can answer gravity strongly enough. A star dies because eventually the balance shifts. When fuel runs low and the old forms of pressure are no longer enough, gravity gains the upper hand. Then matter is forced into states that are much stranger than anything in ordinary life. That is where questions about the limits of pressure stop being hypothetical and become physical. White dwarfs exist because electrons can provide a sort of quantum resistance when ordinary thermal pressure is no longer enough. Neutron stars exist because matter has been squeezed so hard that electrons and protons are no longer content to remain separate in the usual way. These are not casual adjustments. These are fundamental reorganizations under extremes that would make every earthly compression test look like someone leaning on a pillow. And what I find especially satisfying here is that nature does not move directly from everyday matter to complete theoretical madness in one leap. It goes in stages. First, the familiar structures give way, then the atomic picture begins to strain, then quantum rules become the key source of support, then even those forms of support run into their own limits. It is a staircase downward into increasingly severe conditions, and at each step the universe reveals another level of hidden structure. Now, there is a temptation when discussing huge physical limits to imagine matter, as if it were just endlessly squashable, like dough under an increasingly enthusiastic rolling pin. But matter is not passive dough. Matter is built from layers of organization, molecules, atoms, electrons in distinct regions, nuclei, protons and neutrons, quarks inside those. Each layer has its own behavior and its own methods of resistance. When you squeeze matter, you're not simply making the same thing smaller. You're forcing those layers into new relationships. You're changing what kind of thing the matter effectively is. At first, pressure may mostly reduce the gaps between atoms. That is comparatively easy, if easy is the word for anything involving powerful compression. Once those gaps are severely reduced, the electron clouds around atoms begin to interfere more strongly. The matter becomes harder to compress. Press further and atoms can no longer really behave as distinct intact little systems in the usual sense. Their identities begin to blur under the conditions. Go deeper into the cosmic pressure chamber, and you are no longer talking about ordinary matter at all. This is one reason the topic has such a peculiar charm. Pressure sounds like a simple quantity, but it is really a guide to changing regimes of reality. At low levels, it is about material response. At moderate levels, it becomes geology and planetary science. At higher levels, it turns into plasma physics and stellar structure. Higher still, and it becomes quantum degeneracy, dense matter theory, and the strange lives of compact stars. And then, when the pressure becomes so enormous that even our best frameworks begin to quarrel with each other, we arrive at the region hinted at by the word Planck. That word appears in physics whenever we suspect we're approaching a boundary between the well-described and the deeply unknown. Max Planck gave his name to a set of natural scales derived from constants that seem to govern gravity, quantum theory, and relativity. These scales are not arbitrary human units like hours or meters. They are built out of the universe's own bookkeeping. And when physicists speak of a Planck scale for something, they usually mean a scale so extreme that our current theories, taken separately, are no longer enough. So Planck pressure is not merely a pressure that is very large, in the same way a mountain is larger than a suitcase. It is large in a deeper sense. It represents a threshold where the known description of matter, energy and gravity would have to be replaced or completed by something more fundamental. It is the sort of limit that makes physicists clear their throats and become very careful with their wording, because beyond that point the usual confidence begins to thin out. That does not mean the concept is useless, quite the opposite. Extreme limits are often where physics becomes most revealing. Even when we cannot visit such regimes directly, asking what would happen there tells us something important about the architecture of our theories. It is like discovering the weight limit on a bridge you have no intention of driving across with a circus elephant and a tank. The number matters because it tells you what assumptions the bridge was built on. In the case of physics, the bridge is our understanding of the universe, and the circus elephant is gravity behaving very badly indeed. Still, before getting too close to the ultimate limit, it helps to stay with a humble but crucial question underneath it. What is pressure doing to matter in the first place? Why does matter resist? Why is the interior of a planet denser than its outer layers? Why do stars not immediately implode? Why can some forms of matter take astonishing pressure, while others fail early and without dignity? These are not separate questions at all. They are all facets of the same long story. There is also something pleasingly human about this subject. We are creatures who understand the world by pressing on it. Children squeeze mud, stack blocks, stomp snow, poke dough, squash fruit, and sit on things they should probably not sit on. Engineers compress steel samples. Geologists study rocks forged under crushing depths. Physicists build experiments to push matter into more extreme states, and then try not to look too surprised by what comes back. The desire to know how much something can take is old and very recognizable. We ask it of materials, machines, institutions, and unfortunately sometimes ourselves. In physics, though, the answer can be measured, compared, and carried upward into the stars. And what the stars tell us is that matter can take far more pressure than common sense would guess, but not in one simple form forever. Under enough squeeze, matter survives by becoming something else. That is the essential pattern. Ordinary matter yields to denser matter. Denser matter yields to stranger matter. Stranger matter perhaps yields to conditions in which the distinction between matter and the geometry around it becomes harder to discuss with a straight face. The remarkable thing is that all of this begins with a concept simple enough to explain over tea. Pressure is what happens when force is concentrated. Increase the force or reduce the area over which it acts and pressure rises. That is why a sharp heel digs into the floor more than a broad shoe. That is why lying on a bed of nails is survivable under the right conditions, while stepping on one stray nail is a much less charming experience. The idea is straightforward. The consequences are anything but. Because once we leave the scale of household examples, pressure becomes one of the great sculptors of the cosmos. It shapes worlds from the inside. It decides whether a star remains a star. It determines when matter must reorganize into new forms. It draws a path from surface geology to the cores of giant planets, from there to burnt-out stellar remnants, and from there to the doorstep of a much deeper problem. How far can squeezing go before the very language of matter begins to fail us? That is the road we're going to follow. We will begin gently, with pressure in the ordinary sense, because the universe is kind enough to let us approach its harshest truth through familiar experiences. From there we will move inward, downward, and outward all at once, into materials that push back, atoms that refuse to overlap quietly, stars that hold off collapse by the narrowest margin, and finally toward that astonishing upper territory, where Planck pressure sits like a warning sign at the edge of the map. And to make sense of any of that, it helps to start with the basic question hiding in plain sight whenever anything presses on anything else at all. Pressure is one of those words we use so casually that it can seem almost too ordinary to deserve a second look. We talk about feeling pressure at work, pressure in a tire, water pressure in the shower, blood pressure at the doctor, and the pressure of a deadline that has been patiently stalking us for several days. It sounds simple. It sounds familiar. It sounds as though it belongs to the practical side of life, somewhere between kettles, plumbing, and the mild disappointment of discovering that the garden hose has once again been twisted into a shape no natural hose would ever choose for itself. But in physics, pressure is one of those quiet concepts that turns out to be doing far more than it first appears. It sits behind weather and breathing in deep ocean trenches. It helps shape mountains and stars. It explains why some things squash easily, while others barely yield at all. And once we begin asking how much pressure matter can take, we very quickly discover that we cannot really move forward until we slow down and ask what pressure actually is, not in the loose conversational sense, but in the physical sense. What are we talking about when we say that something is under pressure? The first thing to notice is that pressure is not quite the same as force, even though the two are close companions and frequently arrive together. Force is a push or a pull. You lean against a door, press a finger into dough, lift a bag, shove a chair back from the table. In all of those cases, force is involved. Something is being pushed, pulled, lifted, or resisted. Pressure enters the picture when that force is spread over some amount of surface. That detail matters more than it might seem. If you press your hand flat against a wall, you apply a certain force across a broad area. If you press the tip of a pencil against the same wall with the same effort, the force is concentrated into a much smaller region. The pressure is greater, The wall notices the difference. So does your thumb if you are holding the pencil the wrong way around, which is a lesson many people learn once and remember with admirable clarity. This is why snowshoes help someone walk over deep snow without sinking so quickly. They do not make the person lighter. They do not kindly negotiate with gravity on your behalf. They simply spread the person's weight over a larger area, reducing the pressure on the snow beneath. A narrow heel, by contrast, can sink into soft ground with surprising determination, not because the wearer has suddenly gained the mass of a grand piano, but because the force is concentrated through such a small contact point. The ground is being asked to support the same general load in a much smaller place. Pressure, then, is force with a question attached to it. Not merely how hard are you pushing, but how concentrated is the push. That already gives pressure a slightly different personality from force. Force is direct and dramatic. Pressure is more subtle. It is about how insistently a force is delivered. Two people may weigh the same, yet one leaves barely a trace while the other pokes a neat hole in the lawn by virtue of a very enthusiastic shoe choice. Pressure tells us why. It lets us understand why a broad table leg can stand on a wooden floor without trouble, while a pointed object can scratch or dent it with much less effort. It explains why a knife cuts better than a spoon, however energetically you may wave the spoon about. A sharp blade does not magically create extra strength. It simply channels force into a tiny region. The pressure becomes large enough to break the bonds holding the material together, and the cutting begins. This is one reason physics can be both elegant and slightly rude. It takes the romance out of the knife and turns it into a lesson about concentrated force. Still, that is only the macroscopic picture, the large-scale version visible to hands and eyes. Once we shift into the microscopic view, pressure becomes even more interesting. In a gas, for instance, pressure arises because countless tiny particles are moving around and colliding with surfaces. Imagine the air in a room. It seems still enough. It seems empty enough. It certainly behaves as though it is just quietly being there. But on the microscopic level, it is full of molecules darting about in all directions, bumping into one another and into every surface they encounter. When those countless collisions strike a wall, or your skin, or the inside of a balloon, they exert tiny pushes. One collision is nothing to write home about. Trillions upon trillions of collisions happening constantly amount to something very real. That something is pressure. This is a lovely part of physics because it reveals how an apparently smooth and continuous effect can emerge from ridiculous amounts of tiny disorder. Gas pressure does not require the gas to be trying to escape in some dramatic coordinated rebellion. It is not plotting. It is not making plans. It is simply moving, colliding, and transferring momentum over and over again. The result is pressure. That pressure presses outward in all directions. It presses on the walls of a room, the inside of your lungs, the fabric of a cushion, the frame of a window, and the shell of an airplane high above the ground. Most of the time, we barely notice because our bodies and our surroundings are already adapted to living inside this constant bath of atmospheric pressure. We are immersed in it the way fish are immersed in water, though fish at least have the decency to know it is there. The atmosphere above us has weight. That is another fact which sounds obvious and strange at the same time. Air feels light, and in small amounts it is. But the atmosphere is not a small amount. It is an enormous column of gas extending upward for many kilometers, all of it under the pull of gravity. The lower layers support the weight of the air above them, and that gives rise to atmospheric pressure. So when we say there is pressure at sea level, what we really mean is that we are at the bottom of a vast ocean of air, and the weight of that ocean is pressing downward in every direction. Not only downward, interestingly enough, but sideways and upward as well, because pressure in a fluid is transmitted throughout the fluid. A fluid in physics means a gas or a liquid, anything that can flow. That may sound like a dry technical point, but it has wonderfully practical consequences. It is why your ears notice when you go up a mountain or descend in an airplane. The surrounding pressure changes. Your body notices the difference even if your thoughts are currently elsewhere. Water gives us another easy way into the concept because water pressure often feels more intuitive. If you have ever swum to the bottom of a pool and felt the pressure in your ears, or watched a deep sea documentary and felt grateful not to be a small crab living several kilometers below the surface, then you already know the basic idea. The deeper you go, the more water there is above you. The greater the weight of that water, the greater the pressure. Depth brings load. The pressure increases because each lower layer of fluid must support all the fluid above it. That same principle is at work in the atmosphere, though water is denser and makes the point more dramatically. A little depth in water goes a long way. The deep ocean is not merely dark and cold, it is crushingly pressurized. Creatures that live there are not brave in the human sense. They are simply built for a world in which pressure is not an occasional issue but the permanent condition of life. Now, one of the slightly counterintuitive things about pressure is that it can be immense without automatically causing disaster. People often imagine high pressure as something that must instantly flatten or destroy whatever it touches, but that depends entirely on balance. A submarine can survive deep water pressure if its structure can push back with enough strength. Your body survives atmospheric pressure because the fluids and gases within you provide their own internal pressures, and because you developed on Earth rather than dropping in unexpectedly from a pressure-free void looking mildly overwhelmed. Pressure becomes dangerous not simply when it is large, but when there is a large difference between the pressure inside something and the pressure outside it, or when the material involved cannot sustain the imbalance. A balloon bursts not because pressure exists, but because the stretched material can no longer cope with the pressure difference between its interior and its surroundings. A soda can look absurdly sturdy until outside pressure overwhelms the weakened structure and it crumples with all the dignity of a startled accordion. This is worth lingering over because it brings us closer to matter itself. Pressure is not merely something imposed from the outside. Matter also generates internal pressure as part of its own resistance. Compress a gas and the particles have less room to move. Collisions become more frequent. The gas pushes back more strongly. That is why a bicycle pump grows harder to push, as the air inside becomes more compressed. The gas is not being difficult for personal reasons, it is responding according to its nature. Reduce the available volume, and the internal pressure rises. The matter resists further compression. In solids and liquids, the response is different in detail, but the same broad principle remains. Matter pushes back when squeezed. The reason it pushes back depends on its internal structure. In a solid, atoms are arranged in patterns or networks that resist being forced closer together or pulled apart. In some materials, those arrangements are very orderly, in others less so, but either way the atoms are not free to wander around as gas molecules do. They have preferred separations and preferred relationships with their neighbours, set by electrical interactions and quantum rules. Press a solid, and you are trying to disturb those relationships. At first, the material may deform elastically, meaning it changes shape a little and then returns to its original form when the pressure is removed. Push harder, and it may deform permanently. Harder still, and it may fracture. The material response depends on what sort of solid it is and how its internal structure distributes the stress. Metal, wood, glass, rubber, bone and stone all experience pressure, but they do not all answer in the same way. That, in a sense, is the personality of a material. How does it react when reality starts leaning on it? Liquids occupy an interesting middle ground. They resist compression more than gases do, but they flow rather than hold shape like solids. If you press on a liquid in a closed container, the pressure is transmitted throughout the liquid. This is the principle behind hydraulic systems, where pressure applied in one place can be used to produce force in another. Car brakes rely on it. Heavy machinery relies on it. The idea is beautifully straightforward. A fluid can carry pressure through itself. This is why a modest push on one part of a hydraulic system can lead to a much more impressive force elsewhere, provided the geometry is set up properly. It is one of those deeply useful facts that allows civilization to lift large objects without first asking several dozen volunteers to form a complicated lifting committee. And yet, for all these practical examples, pressure becomes most illuminating when we stop thinking about the devices and start thinking about what pressure measures at the deepest level. Pressure measures how matter responds to confinement. That is perhaps the most revealing way to put it for our purposes. If matter is given room, it behaves one way. If it is denied room, it behaves another. Pressure tells us how much insistence is being applied in that denial. It tells us how hard the universe is trying to make matter occupy less space than it would prefer. Sometimes the response is modest, sometimes dramatic. Sometimes the structure of matter itself changes under that insistence. This is why pressure matters so much in planetary interiors and stars. Gravity acts like a relentless confining agent. It keeps pulling matter inward. The matter answers by generating pressure. The whole structure of an object depends on the balance between these tendencies. A planet is not just a pile of material sitting quietly under its own weight. Every layer presses on the layers beneath it. The deeper you go, the greater the pressure, because more and more mass lies above. That pressure can alter minerals, densities, and states of matter. Rocks deep in the mantle are not simply the same rocks found at the surface wearing a heavier coat. They have been changed by the conditions around them. Their atomic arrangements can shift into forms stable only under intense pressure. Matter reorganizes because the environment demands it. The pressure becomes part of the identity of the material. Remove it from that environment and the material may not remain what it was. This point becomes still more striking inside stars, where pressure is not merely a passive consequence of weight, but part of a dynamic struggle against collapse. Gravity pulls inward. Pressure pushes outward. Thermal pressure from hot gas helps support an ordinary star for much of its life. In such an environment, pressure is not a side note. It is one of the main actors. Without it, gravity would simply crush the star inward. With it, the star maintains a rough balance, sometimes for billions of years. That balance is not peaceful exactly, more like a stable argument sustained by enormous energy. But it works. And when the balance fails, the resulting changes in pressure support lead to some of the strangest objects in the universe. Before we get there, though, it is helpful to keep clearing away some common intuitions that can be a little misleading. One is the idea that pressure is always about crushing. Often it is, but pressure is really more general than that. It is about force distributed over area, and that can appear in many forms. Pressure can hold a structure up as well as push it down. It can support, contain, deform, stabilize, or destroy. It can be static, like the pressure in a resting fluid, or dynamic, like the pressure associated with moving air over a wing. It can be external or internal. It can come from thermal motion, gravity, electromagnetic interactions, or quantum effects. The word is simple. The mechanisms behind it are many. Another easy misunderstanding is to picture pressure as something only surfaces feel. Surfaces make pressure easy to visualize, because that is where contact happens in the obvious sense. But inside matter, pressure can describe the state of the material throughout its volume. A gas in a sealed container is not only pressuring the walls, the gas has pressure as part of its condition. The same is true of the matter inside a planet or star. Pressure is not just what one layer does to another. It is also a way of describing the state of the whole interior, the degree to which matter is being compressed, and the intensity with which it resists further compression. This becomes especially important when we ask how much pressure matter can take. The question is not merely how much outside squeezing an object can survive before breaking. It is also about what counts as survival. If a material changes phase under pressure, has it failed or adapted? If atoms lose their familiar arrangements but the matter remains there in a denser state, has the matter been crushed or merely transformed? Once we begin dealing with very high pressures, the line between survival and conversion becomes blurry. Matter does not always stay itself in the everyday sense. It survives by becoming something less familiar. In that sense, high pressure is not always the executioner of matter. It is often the editor. You can see why physicists care so much about this. Pressure is a route into understanding what matter is willing to do when denied space. It reveals hidden structures and hidden limits. Under low pressure, everyday chemistry rules much of behavior. Under higher pressure, chemistry begins to give way to more fundamental interactions. The compressibility of a material, meaning how much its volume changes under pressure, tells us something about the arrangement and flexibility of its internal parts. A gas is highly compressible because there is much room between particles, a liquid much less so, a solid often less again, though the details depend strongly on the material. At extreme pressures, even the categories we are used to begin to lose their tidy boundaries. That gradual stripping away of familiar behavior is what makes the study of pressure so satisfying. It starts from very plain observations. Sharp things cut, heavy things sink, deep water squeezes, pumping air into a tire becomes harder as you go. But then the same idea scales upward into geology and astrophysics. The pressure in the centre of a giant planet is not some completely unrelated concept. It is the same basic physical story told at a far more serious volume. Force distributed through matter, weight bearing down, resistance building up, structure adjusting. A quiet, everyday principle turns out to govern some of the most dramatic environments in existence. And because our subject is ultimately the limit of pressure, it is useful to appreciate just how many different ways matter can answer before it reaches anything like an absolute boundary. Matter can expand, contract, heat up, flow, crack, melt, ionize, rearrange its atomic structure, or enter strange dense states that would have seemed absurd if the universe had not gone to the trouble of making them real. Pressure is the language through which these transitions are negotiated. The higher it climbs, the more basic the terms of the negotiation become. So when we ask what we mean by pressure, really, the answer is richer than a schoolbook definition, even if the schoolbook definition is perfectly sound. Pressure is concentrated force. Yes, it is the result of particles colliding with surfaces. Yes, it is what fluids transmit and what deep water and atmosphere impose. Yes. But it is also the measure of confinement, the physical expression of matter being told to occupy less room and of matter answering according to its structure. It tells us not only how hard something is being pushed, but how close it may be to changing into something else. That is why pressure belongs at the beginning of this whole journey. Before we can talk about planets dense enough to remake their minerals, stars held up by increasingly strange forms of support, or the unimaginable severity suggested by Planck pressure, we need this simple foundation in place. Pressure is the universe pressing the question of space onto matter. Matter responds according to what it is made of and what laws govern it. The deeper and heavier the environment, the more demanding the question becomes, and once that question is asked strongly enough, matter begins to reveal that its ordinary appearance was never the whole story. The first step toward the more extreme answer, then, is to look more closely at that response itself, at the way matter does not merely endure pressure, but pushes back. It is tempting to imagine matter as passive when pressure enters the picture. Something leans on it and it gives way. Something heavier arrives and it gets squeezed. Something large enough settles on top and the story is over. That is how many ordinary scenes look from the outside. A cushion flattens under a tired person. Clay deforms beneath a hand. Snow compacts under a boot. A cardboard box, having made several brave but unrealistic assumptions about its own strength, collapses in the garage. From a distance, it all seems one-sided. Force comes in, matter loses. But that is not really what is happening. Matter is not silent in these encounters. Matter pushes back. In fact, the only reason anything has a shape at all, or remains standing, or does not simply fall through itself in a most unhelpful and alarming way, is that matter is constantly resisting compression, tension, bending, stretching, and collapse. The universe is full of pushing and pulling, but it is also full of response. That response begins at a level so familiar we almost stop noticing it. Put a book on a table, and the book does not continue descending through the wood and onto the floor, then into the soil, and eventually into the sort of geological trouble from which books rarely return in good condition. The table supports it, which is another way of saying the material of the table pushes back against the downward pull of gravity acting on the book. Sit in a chair, and the chair pushes back on you. Lean against a wall, and the wall pushes back on you. Lie in bed, and the mattress pushes back on you, though one hopes with a good deal more kindness than a wall. This is not metaphor. It is the ordinary physical fact that materials resist being compressed into the same space by other materials. At first glance, that seems obvious enough, but it grows far more interesting once we ask how matter manages this. What exactly is doing the pushing back? Why does a steel beam resist more than a pillow? Why does water resist compression far more than air? Why can a diamond remain stubborn under conditions that would leave softer materials feeling deeply unqualified for the job? And why, when pressure becomes extreme enough, do even the strongest familiar materials eventually yield to stranger and stranger forms of resistance? The answer begins with the structure of matter itself. Matter is not a solid, continuous block in the old-fashioned picture one might carry around in the back of the mind. It is made of atoms, and atoms are mostly space in the everyday sense. There is a compact nucleus at the centre, and electrons occupying regions around it. This leads many people to an early conclusion that sounds sensible and is not quite right. If atoms are mostly empty space, then surely matter ought to compress easily. Just squeeze out the emptiness and be done with it. Simple, efficient, very satisfying. Unfortunately for our neat mental shortcut, that is not how atomic structure works. The apparent emptiness inside an atom is not like the empty space inside a cardboard box or between the coils of a spring. It is not unused room waiting patiently to be cleared out. It is part of a delicate arrangement governed by electrical forces and quantum rules. Try to force atoms closer together, and you do not simply remove gaps. You disturb a system that is already balancing several powerful constraints. One of the first reasons matter pushes back is electrical repulsion. Electrons carry negative charge, and like charges repel one another. The electrons around one atom do not greet the electrons around a neighbouring atom with open arms and a willingness to merge politely into a smaller volume. They resist. When two atoms are brought closer together, their electron clouds begin to interfere more strongly. The result is a growing repulsive effect that opposes further compression. This is one reason ordinary matter does not just collapse into a dense, featureless lump. The particles within it are arranged in ways that create resistance long before any dramatic crushing begins. There is a kind of quiet grandeur in that. The firmness of a table, the springiness of a mattress, the bounce of a ball, the rigidity of a building frame. All these everyday experiences are rooted in electromagnetic interactions between atoms. What feels solid to your hand is, at the microscopic level, a huge collective refusal of charged particles to occupy arrangements they do not favour. Solidity is not really the meeting of hard little billiard balls. It is the experience of forces resisting intrusion. When you press your palm against a surface, the atoms in your skin and the atoms in the material do not truly interpenetrate in the ordinary sense. They come close enough for electromagnetic repulsion to become significant, and that is what your nerves interpret as contact. So even the feeling of touch contains a hidden lesson in how matter pushes back. The world feels solid because charged particles are surprisingly opinionated about personal space. This alone, though, is not the whole story. If it were, matter would still resist compression, but not in the full rich way we observe. There is also the quantum nature of electrons themselves. Electrons are not just tiny charged objects orbiting neatly like planets around a sun, however charming that old picture may have been. They are quantum entities described by rules that do not care whether we find them intuitive. One of those rules is especially important for resistance under compression. Electrons cannot all pile into the same identical state. There are limits on how they can be arranged. This means that when matter is compressed, electrons cannot simply all move inward and settle together in some convenient lower space-saving pattern. Available arrangements fill up. Further compression requires electrons to occupy different states, and that costs energy. The matter pushes back more strongly. Even in ordinary solids, this quantum structure helps determine mechanical properties, the strength of chemical bonds, the stiffness of materials, the way crystal lattices hold together. All of it depends partly on the allowed arrangements of electrons. A solid is not strong just because its atoms are present. It is strong because the electrons linking and surrounding those atoms create a stable structure that resists distortion. Press on that structure, and it deforms only to the extent that those relationships can be altered. Sometimes the change is elastic. The solid bends a little, stores energy, and returns to shape when the pressure is removed. Sometimes the atoms slide into new positions and the change becomes permanent. Sometimes the structure breaks altogether. But in every case, what determines the response is the way the matter is organized and the rules governing its particles. This is why materials differ so much in how they push back. A gas pushes back mainly through the motion of its particles. Compress the gas and the particles have less room to move, collide more often, and exert more pressure on their surroundings. A liquid does much the same, but the particles are already closer together and more strongly interacting, so liquids are much less willing to compress. A solid goes further still. Its atoms are locked into more definite relationships, and to compress it significantly you must disturb that whole arrangement. Different solids do this with different levels of enthusiasm. Rubber can deform greatly and still recover, because its molecular chains can rearrange and spring back. Glass resists small deformations well, but may shatter rather suddenly once its tolerance is exceeded. Metals can bend because layers of atoms in their structures can shift while the material remains intact. Diamond, with its rigid bonding arrangement, resists compression remarkably well. Matter pushes back according to its inner architecture. The word architecture is useful here because it reminds us that matter is built, not by an engineer with rolled-up sleeves and a determined expression, but by the laws of physics settling particles into particular arrangements. Some arrangements are spacious, flexible, and forgiving. Others are tight, rigid, and deeply resistant to change. Pressure tests those arrangements. It asks whether the architecture can hold. If it cannot, the matter does not simply vanish. It may crack, flow, transform, or adopt a denser structure. Pushing back is not always a matter of remaining unchanged. Often it means finding a new way to survive the squeeze. There is another player in this story as well, and it is one we touched on earlier in gentler form. Thermal motion helps matter push back. In a hot gas, particles move faster. Their collisions are more energetic. The gas exerts greater pressure for the same confinement than a cooler gas would. This is why heating air in a balloon can make it expand, why steam can drive machinery, and why stars can support themselves for such long periods through thermal pressure generated by the heat of nuclear reactions. Hot matter is restless matter. Its particles do not wish to be crowded, and their agitation contributes to the outward push against compression. That is a useful idea because it shows us that pressure resistance is not always a static property of structure alone. Sometimes it is dynamic. Matter pushes back because its particles are in motion. In everyday life, thermal pressure may be one factor among many. In stars, it becomes one of the main pillars holding the whole object up against gravity. Without the heat generated in their interiors, stars would have little chance of remaining stars for long. Gravity would keep pulling inward, and the matter would need some other form of resistance to avoid collapse. As we will eventually see, when thermal pressure is no longer enough, the universe has stranger backup plans. But for a great deal of cosmic history, heat does much of the work. This leads to an important point about pressure and matter that is easy to miss. Pushing back is not the same as being invincible. Matter resists pressure, but the form and strength of that resistance depend on conditions. Warm gas may push back effectively in one setting and fail in another. A crystal structure stable near the surface of a planet may transform under deeper pressures. A metal beam that comfortably supports a building does not thereby qualify for the centre of Jupiter. Resistance is contextual. Matter answers according to where it is, how hot it is, how dense it is, and how hard it is being pressed. There is no single universal mode of pushing back that works at all scales. In fact, much of the drama of physics comes from the changing ways matter resists as conditions become more severe. At low pressures, molecules and bulk structure dominate the response. At higher pressures, atomic arrangements become the main issue. Higher still, the behaviour of electrons becomes central. Push further and atomic identities themselves begin to blur. Each stage reveals another layer of resistance, another hidden reserve of structure, another way the universe avoids surrendering space too easily. It is rather like packing a suitcase, though on a far more unforgiving and less holiday-oriented scale. At first there is plenty of room and the contents shift around easily. Press the lid down a little and soft things give way. Push harder and you start rearranging items more seriously. Harder still, and you discover that some objects are no longer negotiable, and the whole plan requires revision. Unfortunately, matter under serious pressure does not let you sit on it, while muttering about socks and hoping for the best. It responds according to fixed rules, and those rules become stricter as the available room decreases. This is why compressibility matters so much. Compressibility tells us how readily a material changes volume under pressure. Highly compressible matter gives up space easily. Low compressibility means the matter pushes back strongly as pressure rises. Gases are highly compressible because much of their volume is simply the spacing between particles. Liquids are less compressible because the particles are already crowded close. Solids are often less compressible still, especially if their internal bonding and structure strongly resist rearrangement. Deep inside planets and stars, compressibility becomes a crucial property because it determines how matter responds to the enormous weight above it. If matter were too compressible, objects would be much denser and more compact for a given mass. If it resisted more strongly, internal structures would look different. Whole worlds are shaped by how matter pushes back, and yet even strong resistance can only go so far before the mode of resistance changes. This is one of the key ideas that prepares us for the more extreme parts of the story. When you squeeze ordinary matter, atoms are forced closer together. Eventually, the usual chemical structure becomes less relevant. Electrons are crowded into circumstances where their quantum restrictions dominate the response more strongly than chemistry does. Under enough pressure, matter may become ionized, meaning electrons are no longer attached to individual atoms in the familiar way. Instead of ordinary solid or liquid behaviour, you may get dense plasmas or other exotic states. The material is still pushing back, but it is doing so through deeper rules than the ones responsible for wood, glass or iron behaving as they do on a workshop bench. There is something almost dignified about this progression. Matter does not simply reach a limit and stop. It adapts through layers. When one form of structure can no longer bear the load, another takes over. First, the large-scale arrangement bears it, then atomic bonds, then electron behaviour in a more collective quantum sense. Later, under far more severe conditions, even more fundamental effects join the struggle. Matter keeps finding ways to resist because the laws governing its constituents do not allow arbitrary compression without consequence. This is also where everyday language begins to struggle a little. We speak of pushing back as though matter were an active opponent, perhaps bracing itself with a furrowed brow and a heroic soundtrack. Of course, matter has no intentions. But the phrase remains useful because resistance is real. The world does not yield freely to compression. Space taken up by matter is defended, not by will, but by force laws and quantum principles. That defense is why planets have sizes rather than collapsing into much smaller spheres. It is why mountains can stand, why floors can hold, why stars can maintain balance for long epochs, and why the later collapse of stars into denser remnants is such a spectacular physical event rather than a mundane continuation of the same behaviour. A further subtlety is worth noticing here. Pressure does not only test the material being squeezed, it also tests the pathways through which the material can distribute the load. In a well-ordered crystal, the force may be spread through the lattice in a coherent way. In a flawed material, stress may concentrate around defects and trigger failure earlier. In a layered rock, compression may produce folding or fracture along weaknesses. In a planet, pressure builds with depth, not only because of the total weight involved, but because each layer transmits the burden inward. How matter pushes back is therefore partly about local physics and partly about large-scale structure. The same ingredients arranged differently can answer pressure in very different ways. This is why geology is such an instructive bridge between ordinary matter and the more extreme cosmic settings. Rocks under pressure do not all behave alike. Some deform slowly over immense timescales. Some transform into denser mineral forms, some fracture. Deep in Earth, pressure and temperature together shape the behaviour of the mantle, allowing material that is solid in one sense to flow in another over geological time. Even here on our own planet, far from the most brutal pressures the universe can manage, matter is already showing that pushing back does not always mean staying rigid. Sometimes resistance means changing form without losing continuity. Sometimes it means flowing so slowly that from a human perspective it seems still, while over millions of years it behaves almost like an immensely patient liquid. The same general truth extends outward to more massive worlds. Increase the size of a planet and its interior pressure rises. The deeper regions are forced into denser states. Materials that would be perfectly ordinary near the surface become something else far below. In gas giants, pressure and temperature become so intense that matter enters forms with properties unfamiliar on Earth. The stuff pushes back, but not in the same style as a piece of rock or a steel bar. Gravity keeps demanding tighter packing, and matter keeps revising its answer. That changing answer is really the heart of the matter. Pressure is not merely an external squeeze. It is an ongoing conversation between confinement and resistance. Matter replies in the language available to it at that depth, density and temperature. At first the reply may be mechanical, then chemical, then atomic, then quantum in a more dramatic sense. The deeper we go into serious compression, the less useful our everyday categories become, and the more we're forced to think in terms of the underlying rules. Perhaps that is why this subject feels so satisfying once you settle into it. Something as simple as pushing on an object turns out to be connected to the deeper structures of matter. The firmness of your chair, the compression of air in a pump, the shape of Earth, the survival of giant planets, the support of stars, all are part of the same broad story. Matter does not accept confinement without reply. It always answers. The details of the answer tell us what kind of matter we are dealing with, and how extreme the circumstances have become. And when the circumstances become truly vast, as they do inside worlds much larger than our own, this quiet pushback starts shaping entire planets from the inside out. Their layers, densities, mineral forms and hidden interiors all emerge from the long contest between gravity bearing down and matter refusing to become smaller without a fight. That quiet refusal becomes much easier to appreciate when we stop looking at objects on tables and start looking at worlds. A planet is, in one sense, an enormous pressure experiment conducted by gravity over a very long time. Gather enough matter into a roughly spherical shape, let gravity pull every part toward the centre, and pressure begins to build automatically. No engineer needs to switch anything on. No cosmic hand needs to turn a dial. Weight accumulates above weight, layer above layer, and the interior is forced to support everything resting on top of it. The deeper you go, the greater the burden, and the matter below can only respond by pushing back in whatever way its structure allows. This is what makes planets such marvellous physical objects. From a distance, they look serene. They drift along in their orbits, minding their business, presenting smooth cloud bands or quiet rocky surfaces, or the occasional ring system that seems frankly a little showy. But beneath that calm exterior, every sufficiently massive world is under stress. Its interior is not just sitting there. It is being pressed from all sides by the simple fact of its own existence. A planet does not need an external crusher. It carries the crusher within its own gravity. Here on Earth, we live on the very outer skin of that arrangement, which is one reason our intuitions about planetary pressure are not always especially good. The surface feels solid enough. Mountains stand, buildings hold, and the ground underfoot rarely gives the impression that it is currently participating in a grand compression drama. Yet descend into the planet, and the conditions change steadily. Every kilometre downward adds more overlying rock. More weight means greater pressure. That pressure alters the behaviour of the material below, sometimes gradually, sometimes by pushing it into entirely new forms. One of the first useful things to notice is that pressure inside a planet does not increase, because the matter at the centre is somehow trying harder than the matter near the surface. The reason is simpler and more merciless. The central regions are carrying the load of almost the whole planet above them. Near the surface there is comparatively little overburden. Deeper down, there is more and more. By the time you reach the central parts of a large planet, the pressure has become extraordinary, not because the material there is special to begin with, but because gravity has spent billions of years leaning on it with relentless consistency. This gradual build-up of pressure shapes planetary interiors in ways that are easy to underestimate. Rocks at the surface behave like the rocks we know. They crack, weather, crumble, melt if heated enough, and generally cooperate with geology in ways that feel familiar. But the same chemical ingredients, once buried deep enough, may adopt different crystal structures under pressure. This is one of the most important lessons of deep planetary science. Material is not defined only by what it is made of. It is also defined by the pressure and temperature under which it exists. A mineral stable in the shallow crust may not remain stable deep in the mantle. Under enough compression, its atoms can rearrange into a tighter, denser form. This does not mean the substance becomes unrecognizable in every sense. It means that pressure forces the atoms into a new pattern, one better suited to the cramped conditions. The matter pushes back, yes, but it also adapts. It gives up the arrangement that worked near the surface and adopts one more comfortable for life under enormous burden. Deep planetary interiors are full of this kind of forced compromise. Matter survives by becoming denser and structurally different. Our own planet offers a beautiful example of this layered transformation. Earth is not a uniform ball of rock with a bit of scenery painted on top. It has a crust, a mantle, an outer core and an inner core, each with different properties and behaviours, and pressure is one of the reasons those distinctions exist. The crust is thin and relatively cool compared with what lies below. The mantle is made of solid rock, but over immense timescales it can flow. That last part is always worth pausing over, because it sounds suspicious at first. Solid rock that flows. It seems like the sort of statement designed to make a schoolchild distrust science forever. But under the temperature and pressure conditions of the deep mantle, and over geological time, rock can indeed deform and creep. It does not flow like tea. More like a substance with an extremely patient agenda. As depth increases through the mantle, both pressure and temperature rise. The minerals there respond by changing form. Their atomic arrangements pack more tightly. Density increases. The material remains solid but not unchanged. Then, deeper still, Earth reaches its core, where the story changes again. The outer core is liquid, composed mainly of iron and nickel with some lighter elements mixed in. Deeper still lies the inner core, solid despite the immense heat, because the pressure is so great that it forces the material into a solid state. This is one of those planetary facts that feels almost backwards the first time you hear it. The deeper region is hotter and yet solid, while the somewhat shallower region is liquid. The reason is pressure. The centre, the squeeze is so intense that the atoms are held in a solid arrangement despite the temperature trying its best to encourage a more fluid lifestyle. That alone should tell us how powerful planetary pressure can be. It does not merely crack rocks or compact sediments. It can decide whether matter is solid or liquid under conditions where temperature alone would suggest otherwise. Pressure is not a detail in the physics of planets. It is one of the main authors. Even so, Earth is only a modest example compared with the larger worlds in our solar system. The giant planets take the same basic principle and raise it to far more intimidating levels. Jupiter, for instance, is mostly made of hydrogen and helium, substances that on Earth are associated with balloons, laboratory tanks, and the general impression of being rather insubstantial. But inside Jupiter, those same ingredients exist under such extreme pressure that hydrogen begins to behave in extraordinary ways. Deep below the cloud tops, hydrogen is compressed until it becomes a liquid, and deeper still, it is believed to enter a metallic state. Metallic hydrogen is one of those phrases that sounds like two different subjects accidentally wandering into the same sentence, but it captures something very real. Under sufficiently high pressure, hydrogen can conduct electricity like a metal. This is one of the delights of planetary physics. Materials that seem simple and familiar at the surface become strange under pressure. Hydrogen, the lightest element, turns into something far removed from the gas that floats a party balloon toward the ceiling, and then spends the rest of the afternoon hovering there in a rather self-satisfied way. Pressure changes the rules of behaviour. It reveals possibilities hidden at ordinary conditions. In Jupiter and Saturn, this is not some laboratory curiosity, but part of the actual deep interior structure of worlds larger than anything rocky. Once you start thinking this way, planets become less like static objects and more like pressure sculptures. Their mass determines how hard gravity squeezes. That squeeze determines how density changes with depth. It determines what phases of matter can exist. It determines whether the interior is layered sharply or gradually, whether convective motions can occur, whether a core remains molten, and how the planet evolves over time. Even a planet's magnetic field can depend on these internal pressure-driven arrangements, because magnetic fields often arise from the motion of conducting material in the deep interior. Smaller rocky bodies show the same principles more modestly. The Moon, for example, is much smaller than Earth, so its internal pressures never reach the same extremes. That helps explain why it cooled more quickly and became geologically quieter. Mars is larger than the Moon, but still much smaller than Earth, and its interior tells a different story again. Planetary size matters because size controls how much self-compression occurs. More mass means stronger gravity. Stronger gravity means higher internal pressure. Higher internal pressure means more dramatic material responses. Worlds of different sizes are not simply scaled versions of one another. They become physically different environments because pressure remakes their interiors. This becomes especially important when scientists think about worlds beyond our solar system. Many of the planets discovered around other stars are larger than Earth but smaller than Neptune, a class of worlds for which we do not have a neat everyday analogy. Some may be rocky super-Earths. Some may contain thick layers of water in exotic high-pressure forms. Some may have deep atmospheres above compressed interiors. In all such cases, pressure is central to understanding what those worlds are really like. A planet somewhat larger than Earth does not merely have more ground. Its deep interior may experience pressure sufficient to create mineral phases absent from our own planet, or present only in its deepest regions. Matter there may be packed into states that reshape the whole planetary structure. This is where the phrase crushing worlds begins to feel less dramatic and more descriptive. Planets really are crushed by their own gravity, though the crushing is balanced by the way matter pushes back. If there were no resistance, planets would continue collapsing until something much stranger resulted. Their actual size is a compromise between gravity pressing inward and matter resisting compression. For smaller rocky planets, this compromise allows a relatively familiar structure. For larger and more massive worlds, self-compression becomes stronger, and the average density can rise even if the overall composition remains similar. The world becomes more compact not merely because it has more stuff, but because the added gravity squeezes that stuff harder. There is something very elegant in that. Gravity is simple in its intention. It pulls mass together. But the result is not simple, because matter has an internal life. It resists in different ways depending on pressure, temperature, and composition. A planet is the visible result of this long argument. Its radius, layering, and deep behavior all emerge from the conversation between gravitational demand and material refusal. Pressure also works closely with temperature, and the two are not easy to separate in real planetary interiors. As material is compressed, it can heat up. As planets form, collisions and sinking heavy elements generate heat. Radioactive decay may add more. That heat can melt regions, drive convection, and alter material behavior. Pressure alone might encourage one structure while temperature encourages another, and the actual interior state reflects their competition. This is why the same substance can behave very differently in different planetary settings. A given mineral deep in a cool world may not resemble what it would do in a hotter one at comparable pressure. Matter responds to the full environment, not just one variable. This becomes particularly fascinating in worlds with large amounts of water or ice. On Earth, water is so familiar that it's easy to forget how varied its behavior can become under pressure. We know it as liquid, ice, and vapor. But under high pressures it can form several different solid phases, each with a different arrangement of molecules. In the deep interiors of icy moons or water-rich exoplanets, water may exist in dense ice forms that have little in common with the frost on a window, or the cubes in a kitchen freezer. The phrase ice still applies, but the reality is much stranger. Again, pressure has forced a familiar material into an unfamiliar structure. If this all sounds rather severe, it is because planets are, in their deep interiors, severe places. Yet there is also something calm about the way nature handles these extremes. Pressure rises smoothly with depth. Materials shift phase when conditions require it. Layers differentiate. Heat flows outward. Convection stirs what can move. The whole system evolves according to the same general laws. No drama is needed even when the conditions would flatten every ordinary object we know without the slightest hesitation. And still, for all their intensity, planets remain in some sense only the middle ground of the pressure story. They are already extraordinary by human standards, but not by the standards of the cosmos at large. The centre of Earth is a place of astonishing pressure compared with anything at the surface, yet it is still only a beginning when placed beside what happens in the remnants of stars. That is worth remembering because it helps us keep our scale straight. The pressure inside planets is enough to alter minerals, reshape matter, create metallic hydrogen, and decide the state of planetary cores. It is enough to build magnetic fields and sculpt whole internal architectures. It is enough to make a world fundamentally different from its surface appearance. But it is not yet enough to force matter into the truly exotic forms found in compact stellar remnants. Even so, planets teach the essential lesson better than almost anything else. Pressure is not just a number on an instrument, it is an organizing principle. Inside a planet, pressure decides what materials can exist, where they can exist, and how they will behave once there. It makes deep interiors denser than outer layers. It drives structural transitions. It creates worlds within worlds, hidden beneath the visible surface. If you could somehow descend through the layers of a large planet without the whole business ending very badly, you would not simply be moving deeper into more of the same. You would be passing through a sequence of environments, each produced by greater confinement, each demanding a different response from matter. And that really is the larger theme quietly building beneath all this. As pressure rises, matter does not merely endure, it becomes less ordinary. The comfortable atomic arrangements of the surface world give way to denser patterns. Familiar materials turn into less familiar ones. Simple substances reveal unexpected behaviours. And if pressure keeps rising far beyond the scale of planets, even atoms themselves begin to find the situation increasingly difficult to maintain in the usual way. The squeeze grows so intense that matter must start surrendering some of the structures we take for granted, beginning with the ordinary integrity of the atom itself. By the time pressure has built itself into the deep interiors of worlds, matter is already behaving in ways that would seem quite unreasonable at the surface. Rocks change their crystal structures, metals respond differently to heat and confinement. Hydrogen, which most of us would not normally nominate as a candidate for dramatic reinvention, can be forced into metallic behaviour. All of that is strange enough. But there comes a point where pressure stops merely rearranging the furniture of matter and begins interfering with the house itself. That is when atoms begin to surrender. The word surrender may sound a bit theatrical, as though atoms are waving tiny white flags, while gravity advances across the field with a very serious expression. But it captures something important. Under ordinary conditions, atoms are stable units of matter. They bind into molecules, arrange themselves into solids, float around in gases, trade electrons, form chemical bonds, and generally carry on as distinct little citizens of the material world. Chemistry depends on that distinctness. So do most of the things we call ordinary matter. Wood, water, salt, iron, skin, air, glass, bone, granite and tea all rely on atoms maintaining their identities well enough to participate in familiar structures. Pressure can disrupt that identity, not all at once and not in some sudden theatrical explosion of atomic despair, but steadily, insistently, by crowding atoms into conditions where the usual arrangement can no longer hold. That is the crucial idea. Atoms are not invulnerable building blocks that remain unchanged no matter what environment they find themselves in. They are stable only within a range of circumstances. Squeeze matter hard enough, and the atom, which seemed so self-contained and reliable near the surface of a planet, starts to lose the very features that made it atom-like in the everyday sense. To see why, it helps to remind ourselves what an atom actually is. It is not a miniature solar system with electrons orbiting a nucleus in tidy little loops like dutiful planets. That picture has a certain charm and a useful historical role, but it is not how atoms really behave. Electrons occupy quantum states around the nucleus. Their behaviour is governed by probability, energy levels and rules that are only loosely related to anything visible in daily life. An atom has structure, but that structure is not mechanical in the ordinary sense. It is a balance of electromagnetic attraction, quantum restrictions, and allowable arrangements. Under normal conditions, this balance works beautifully. The nucleus, positively charged, attracts the negatively charged electrons. The electrons do not simply crash inward because quantum physics does not allow that neat little catastrophe. Instead, they occupy states that give the atom its characteristic size and behaviour. Different atoms have different numbers of protons and electrons, and so different sets of possible arrangements. That is where chemistry comes from. Carbon behaves like carbon because its electrons are arranged in a particular way. Oxygen behaves like oxygen. Iron behaves like iron. The whole richness of the material world depends on these distinctions holding up. Now, if you look at an atom and notice that much of its volume is not occupied by a dense little lump, it is tempting to think this means atoms should be easy to compress. After all, if something is mostly empty space, surely pressure can simply squeeze that space away. But the word empty here is misleading. The region around the nucleus is not empty like an unused room or the gap between books on a shelf. It is occupied by the quantum presence of electrons. It is part of the atom's actual structure. You cannot simply remove that space without altering the atom itself. As atoms are pushed closer together, their electron regions begin to overlap more strongly. This is where the first serious trouble begins. At moderate pressures, the overlap may merely alter bonding and material properties. At higher pressures, it becomes increasingly difficult for the atoms to behave as separate units with well-defined outer electrons. The electron structure that once allowed neat chemical identities becomes distorted by crowding. In effect, the atoms are being told that the comfortable spacing required for their ordinary lives is no longer available. This does not immediately destroy them. Matter is annoyingly resourceful. Instead, the system adapts. Electrons may become less tightly associated with individual nuclei. Chemical bonds may change. Solids may adopt denser phases. Electrical properties may shift. The material begins to move away from ordinary chemistry and toward a more collective form of behavior. This is why high-pressure matter often does not resemble the familiar substance we started with, even if the ingredients are technically the same. The atom is still present in some partial sense, but its role is changing. It is no longer the polite discrete unit it once was. A useful comparison might be a crowded train platform, though with fewer complaints about schedules and a good deal more quantum mechanics. If there are only a few people, everyone can stand in a comfortable way, maintain a bit of distance, and keep their belongings to themselves. As more and more people are forced onto the platform, those neat arrangements vanish. Personal space disappears, distinctions blur. Movement becomes collective and constrained. At some point, the idea of individuals occupying their preferred spot stops being a realistic description of what is happening. Something like that occurs when atoms are forced close enough together. Their electrons can no longer remain neatly organized in the familiar atomic way. One of the most important steps in this surrender is ionization under pressure. We often think of ionization as something caused by heat or radiation, and that is certainly true in many situations. Heat can knock electrons loose, radiation can strip them away, but pressure can also do the job by crowding atoms so tightly that electrons are no longer best described as belonging to one atom at a time. This is sometimes called pressure ionization, and it marks a major change in the nature of matter. Once electrons are no longer attached in the ordinary way, the system ceases to behave like a collection of normal atoms. It becomes something more like a dense plasma or an electron-rich fluid with nuclei embedded in it. At that point, chemistry begins to lose authority. This is one of the key transitions in the whole story of extreme pressure. Chemistry rules much of everyday matter because atoms and molecules preserve their identities well enough for bonding patterns to matter. But under sufficient compression, the distinctions between atoms become less significant than the collective behavior of electrons and nuclei packed into a small volume. The material is still matter, of course, but it is no longer matter in the ordinary chemical sense. It has crossed into a regime where the old language starts to sound inadequate. Pressure is especially good at creating this sort of transition because it acts directly on spacing. Heat makes particles move more energetically. Radiation can alter internal arrangements. Pressure says something more basic. There is less room now. Make it work. That demand forces the issue. If atoms require a certain amount of space to maintain their ordinary structure, and that space is denied, then a new regime must emerge. The atom does not decide to surrender out of weakness. It surrenders because the rules of stability have changed. This is one reason the deep interiors of giant planets are so interesting. They occupy the middle territory between everyday condensed matter and the truly exotic matter of stellar remnants. There, pressure is high enough to force major changes in atomic behavior without yet reaching the extreme conditions of a white dwarf or neutron star. It is a kind of warning zone, where the atom begins to discover that it is not the final stable unit it imagined itself to be. Hydrogen is the most famous example, because under such compression, its electrons can become delocalized, allowing it to conduct electricity like a metal. But the broader lesson applies to matter generally. Given enough pressure, atomic individuality starts to fail. That phrase, atomic individuality, may sound slightly philosophical for a subject involving very serious compression, but it is exactly what is at stake. What makes one atom distinct from another in a material is not just the nucleus at the centre, but the arrangement of electrons around it and the way it can bond and interact. Once extreme pressure interferes with those arrangements, the atom ceases to function as the same kind of entity. It becomes part of a denser and more collective state. The nucleus is still there. The protons and neutrons have not yet been forced into a more radical change. But the atom as a chemical actor is fading. There is something almost melancholy about that if one is inclined to be sentimental about atoms, which I would not recommend as a lifestyle, but will allow as an occasional late evening indulgence. The ordinary atom is such a successful invention of nature. It gives us the periodic table, molecules, materials and life itself, and it allows the whole elaborate surface world of chemistry to exist. Yet in the deeper and heavier parts of the universe, this arrangement is treated not as sacred, but as conditional. It works where it works. When pressure becomes overwhelming, it is set aside. Still, surrender is not annihilation. That is important. Matter does not simply disappear once atoms lose their ordinary form. Rather, new forms of support and organisation begin to matter more. The electrons that once defined chemical behaviour now begin to act collectively in ways that can resist further compression. The nuclei remain as dense positive centres embedded in this more shared electronic environment. The story shifts from chemistry to dense matter physics. It is less about molecules and more about packed particles under severe restriction. At the same time, temperature often joins the story. In many high-pressure environments, especially in planets and stars, matter is not only compressed but heated. The combination can make atomic surrender even more complete. Heat agitates particles and can strip electrons loose. Pressure denies room and forces overlap. Together they turn ordinary matter into ionized matter. This is why so much of the visible universe is actually plasma rather than the tidy neutral atomic material we tend to picture when thinking about solids and gases. Stars, for example, are largely made of plasma, not ordinary gas in the surface world sense. Their atoms have long since ceased to keep all their electrons in the usual way. Yet even stellar plasma, hot and ionized though it is, does not represent the furthest consequence of atomic surrender. In an ordinary star, atoms lose their everyday identity, but thermal pressure from the hot particles can still provide much of the resistance against gravity. As long as nuclear reactions keep the interior hot enough, the star can maintain a kind of balance. The atoms are no longer living chemical lives, but the matter still has room enough and energy enough for thermal motion to matter greatly. The real crisis comes later, when a star exhausts the fuel that allowed that thermal support to continue. Then gravity presses harder in a different sense, not necessarily because the star suddenly becomes more massive, but because the support weakens. The inward pull is no longer matched by the same outward thermal pressure. Matter begins collapsing into denser states. The electrons, already freed from ordinary atomic duty, are forced into even closer quarters. This is where atomic surrender gives way to something more consequential. Once atoms are gone as meaningful structural units, the electrons themselves become the next line of resistance. That transition matters enormously, because it reveals a hierarchy in the way matter responds to pressure. First, bulk structure resists, then chemistry and ordinary atomic arrangements. Then, when those fail, the behaviour of electrons as quantum particles becomes the relevant support. At each stage, pressure strips away one layer of familiar organisation and exposes a deeper one beneath it. It is a little like peeling back the visible world to reveal the principles underneath, except that in this case the peeling is being done by gravity, with extraordinary force and no interest whatsoever in our comfort. Even before we reach white dwarfs, though, the lesson is already clear. The atom is not a permanent fortress. It is a stable pattern within a certain regime. It survives surface conditions, laboratory conditions, even many planetary interiors, but under enough pressure, the arrangement breaks down. Electrons can no longer stay neatly assigned. chemical properties lose meaning, matter becomes denser, more collective, less ordinary. The things that once defined the material world of tables, oceans, bones, and atmosphere begin to fade into irrelevance. This is also why the phrase crushed matter can be slightly misleading. It suggests that pressure simply squashes things flatter and flatter while leaving their identity intact. What actually happens is more subtle and more interesting. Pressure changes what kind of thing the matter is. A compressed atom is not just a smaller version of an ordinary atom. Past a certain point, the very concept stops being useful. The system has moved into a new regime. That is what surrender really means here. Not destruction for its own sake, but the loss of one stable description and the need for another. The deep interior of a giant planet, the burning core of a star, the collapsing remains of a stellar life, these are all places where matter is being asked to give up the comforting arrangement we see around us. Atoms do not object in words, of course. They simply cease to behave as atoms in the everyday sense. Their electrons become communal, their chemistry dissolves, and the material enters a harsher domain where space is precious, and ordinary structure has no authority. And once you arrive there, an intriguing reversal occurs. The very electrons that could no longer preserve the ordinary atom begin to provide a much stranger and more formidable form of resistance. They stop being the quiet bookkeepers of chemistry and start becoming the source of an altogether deeper pressure, one that can hold up the remnants of dead stars against collapse for astonishing lengths of time. That deeper pressure is where the story becomes properly strange, because it no longer comes from heat in the familiar way, or from ordinary atoms keeping their polite distance, or from chemical bonds trying to preserve the arrangement we know from everyday life. It comes from a rule that sits much deeper than any of those. A rule that does not care whether matter is comfortable or hot or elegant or easy to picture. It simply says that certain particles cannot all occupy the same state at once. And from that rule, under the crushing conditions left behind when a star begins to collapse, there emerges one of the most remarkable forms of resistance in the universe, degenerate matter. Now, the word degenerate is unfortunate if you happen to be meeting it outside physics for the first time. It sounds judgmental. It sounds like matter has made some poor life choices and is now being spoken about in disappointed tones by a committee. But in physics, it means something far more technical and much less scandalous. Degenerate matter is matter so densely packed that the usual ways particles arrange themselves are no longer governed mainly by temperature or ordinary chemistry, but by quantum restrictions. In plainer language, it is matter under such severe crowding that the rules of available arrangement become the main source of pressure. This is one of those ideas that can feel slippery at first because it does not match our ordinary experience. When we think of pressure, we usually think of particles moving around and banging into things. Hot gas in a container pushes on the walls because the particles are darting about and colliding with everything in sight. Make the gas hotter and the particles move faster, so the pressure increases. That all feels sensible. The pressure comes from motion, from thermal agitation, from the restless energy of a system not sitting still. Degenerate matter pushes back even when that kind of thermal motion is no longer the main story. That is the part that catches people. It is a kind of pressure born not mainly from heat, but from the fact that particles called fermions are not allowed to pile into the same quantum arrangement. Electrons are fermions. So are protons and neutrons, and this restriction matters enormously when matter is compressed to extraordinary densities. A helpful way into it is to imagine a crowded building with many floors and many rooms. In ordinary circumstances, people can spread out however they like. Plenty of room, no need to stack everyone tightly. But if more and more people are forced into the building, and there is a strict rule that only a limited number can occupy each room, then the later arrivals cannot simply squeeze into the same places as the others. They must move into higher and less convenient rooms. Keep forcing more people in, and you create pressure, not because they are all running around in a panic, but because the allowed arrangements are filling up. The crowding itself creates a kind of structural resistance. That analogy is imperfect, as all analogies eventually are once quantum mechanics arrives and begins rearranging the furniture, but it points in the right direction. In a dense collection of electrons, the lowest available states fill first. Additional electrons must occupy different states. As compression increases and the available volume shrinks, the electrons are forced into a more and more constrained set of possibilities. The matter pushes back because further compression would require forcing electrons into still more extreme arrangements. That requirement carries energy, and the result is pressure. This means that the strength of degenerate matter does not depend in the ordinary way on keeping the material hot. A star like the Sun supports itself largely through thermal pressure. It is hot enough in the core for particles to move furiously and for nuclear reactions to keep that heat replenished. But once a star has exhausted the fuel needed to sustain that kind of support, gravity begins to win ground. The star contracts, densities rise, atoms are long gone as ordinary atoms. Electrons are now moving in a dense collective environment. And eventually the electron crowding becomes so severe that degeneracy pressure takes over as the main resistance. There is something deeply satisfying about this. When one source of support fails, the universe reveals another one hidden underneath. First heat and ordinary particle motion do the work. When that is no longer enough, the quantum restrictions on electrons step forward, not because they were waiting heroically in reserve, but because the conditions have finally become severe enough for their influence to dominate. Matter survives by invoking a deeper law. This is why the phrase strange strength feels appropriate. Degenerate matter is strong in a way that is not obvious from the everyday behaviour of materials. A steel beam is strong because of how its atoms are bonded and arranged. A rock is strong because of its structure and chemical composition. But degenerate matter is strong because the particles inside it are forbidden from all settling into the same convenient state. It resists compression at a level deeper than ordinary material engineering. You're no longer dealing with a familiar solid or liquid in the surface world sense. You are dealing with matter whose stiffness comes from quantum crowding. That crowding can support astonishing loads. Consider what happens in the remnant core of a star that has shed its outer layers and collapsed inward. Gravity continues pressing inward because gravity is, if nothing else, very consistent. The matter becomes incredibly dense, yet instead of collapsing without limit, the core can stabilize. Not because it has become especially hot in the ordinary supporting sense, though it may certainly be hot. Not because atoms have somehow become tougher than expected, but because the electrons are packed into such a dense state that their degeneracy pressure can balance gravity. The result is a white dwarf, one of the most extraordinary objects in the universe. A white dwarf is not large by stellar standards. It is roughly Earth-sized in radius, yet contains a mass comparable to that of a star. This means its matter is packed to a density that would make ordinary intuition sit down quietly in the corner and reconsider things. A spoonful of white dwarf material, if such a thing could be brought anywhere without the whole arrangement becoming both impossible and catastrophic, would weigh an absurd amount by everyday standards. But the truly important point is not just the density, it is what is holding the object up: electron degeneracy pressure. This leads to one of the most curious consequences in all of astrophysics. For ordinary objects, adding more mass usually makes them larger, at least if the material type stays broadly similar. More clay makes a bigger lump. More water fills a bigger tank. More rock makes a bigger hill, assuming geology cooperates. White dwarfs do not follow that friendly intuition. Add more mass to a white dwarf and gravity compresses it further. The electron degeneracy pressure rises in response, but the object actually becomes smaller. More mass means more inward pull, which means more severe compression, which means a smaller and denser white dwarf. It is one of those facts that seems designed specifically to remind us that compact objects do not care about human expectations. The reason this happens is bound up with the nature of the degeneracy pressure itself. The more tightly you pack the electrons, the fewer low-energy states remain available, and the more the electrons are forced into higher and higher momentum states. The system pushes back more strongly, but the price of support is increasing density. The object can remain in equilibrium, but only by becoming more compact. It is a remarkable compromise between quantum rules and gravity. Gravity demands tighter confinement. The electrons answer with stronger degeneracy pressure. The stable result is a smaller, denser star remnant. There is also a lovely austerity to white dwarfs. They are no longer making new energy through nuclear fusion in the way ordinary stars do. They shine mainly because they are still hot from their earlier history, and cool only gradually over immense stretches of time. Their pressure support is not tied to active burning in the core. It is structural, rooted in the dense quantum state of the electrons. They are like embers of stellar evolution held up by a rule deeper than flame. And yet, strong as our electron degeneracy pressure is, it has limits. This matters because it tells us that even degenerate matter is not the final answer to compression. If a white dwarf becomes too massive, electron degeneracy pressure can no longer support it. Gravity presses too hard. The electrons are forced into conditions where the balance breaks down. This upper limit is one of the great thresholds in astrophysics, and it determines whether a stellar remnant can remain a white dwarf or must collapse further into something even stranger. But before going that far, it is worth staying with the physics of the pressure itself, because it is one of the clearest examples of how quantum rules can produce large-scale physical consequences. Degeneracy pressure is not a tiny correction. It is not some obscure footnote operating quietly in the margins while gravity and temperature do the real work. Under the right conditions, it becomes the dominant source of support for an entire star remnant. That is a stunning thing to pause over. A rule about what electrons are allowed to do in quantum states determines the fate of stellar corpses. It shapes the size of white dwarfs. It decides whether collapse can be halted. A microscopic principle governs a macroscopic world. This is a recurring pattern in physics, but it never really stops being impressive. The large and the small are tied together more tightly than common sense first suggests. The comfort of a chair depends on atomic forces. The structure of a crystal depends on electron arrangements. The fate of a dead star depends on the exclusion principle. Nature keeps making this point in larger and larger handwriting. There is another subtle feature of degenerate matter that makes it different from ordinary material strength. In everyday substances, heating often changes the mechanical response significantly. Heat a solid enough, and it softens or melts. Cool a gas, and its pressure drops if the volume stays the same. Thermal behavior matters. In degenerate matter, once the density is high enough and the degeneracy is strong enough, the pressure depends much less on temperature than ordinary pressure does. The key variable is the density and the filling of available states. This is why degenerate matter can support itself even as the object cools. The pressure is not mainly coming from thermal agitation that must be constantly replenished. It is built into the dense quantum arrangement. That gives white dwarfs a kind of durability that ordinary stars do not possess in the same way. An ordinary star needs ongoing fusion to maintain its internal thermal pressure. Shut that off, and the structure changes dramatically. A white dwarf, once formed, does not require a furnace in the middle to hold itself up. Its support comes from the packed electrons themselves. Cooling changes its glow, but not the essential source of pressure. It is a very different kind of equilibrium, less lively, perhaps, but deeply stable within its allowed mass range. At the same time, calling degenerate matter strong should not tempt us into picturing it as hard, in the way a hammer or diamond is hard. These familiar words begin to wobble under such conditions. White dwarf matter is not a household material with a superior rating. It exists under circumstances where the entire object is held together by gravity and supported by quantum pressure. If you could somehow remove a piece of it from that environment, the piece would not sit there politely behaving as a tiny white dwarf brick. It would undergo radical change because the surrounding conditions that made the state possible would no longer hold. This is true of many extreme forms of matter. Their properties are inseparable from the environment in which they exist. That is another useful lesson. Strength in physics is not always an intrinsic quality detached from circumstance. It often depends on context. Degenerate matter is astonishingly resistant to compression under the conditions of a compact stellar remnant, but the whole arrangement is part of a global balance involving gravity, density, and quantum rules. The object is stable because everything is in the right relation. Remove that relation and the description changes. This way of thinking helps us avoid turning exotic matter into myth. White dwarfs are not magical. Degenerate matter is not mystical. It is simply the natural result of known physics pushed into a very severe regime. We are used to materials whose behaviour is dominated by chemistry and thermal motion. White dwarfs live in a regime dominated by quantum crowding and self-gravity. Different rules become central, but they are still rules. Strange? Yes. Arbitrary? No. And once you become comfortable with that, another idea starts to feel less outrageous. If electron degeneracy pressure can support a white dwarf, then perhaps under still more severe compression there may be another stage waiting below it, another deeper layer of matter's resistance. After all, if gravity can overcome the electron-based support, the collapse does not immediately become meaningless. The matter must answer again, but with a different set of particles and a still harsher form of crowding. The electrons, having held the line as long as they can, are eventually forced into a new relationship with the nuclei. The structure of the matter changes again. The next stage of resistance belongs not to electrons, but to matter compressed so deeply that the star remnant becomes an altogether darker and denser kind of object. Before that transition arrives, though, it is worth appreciating what degenerate matter has already shown us. It has shown that matter can push back in ways completely hidden from everyday experience. It has shown that the ordinary atom is not the last meaningful unit in the story. It has shown that a star can die, lose its familiar source of support, and still avoid immediate total collapse because quantum mechanics has one more card to play. Most of all, it has shown that pressure is not merely something matter suffers. Under the right conditions, pressure reveals a secret reserve of resistance woven into the deepest rules of particle behaviour. That reserve is powerful enough to hold up a white dwarf for billions upon billions of years. But gravity is patient, and nature is not finished revealing how far this ladder of compression can descend. The moment electron degeneracy pressure reaches its limit, the struggle enters an even more severe stage, where the fate of a collapsing star depends on whether matter can find yet another way to push back against the weight of its own ruin. What makes a white dwarf so compelling is not just that it is dense, or hot, or the leftover heart of a dead star. It is that a white dwarf is a compromise, a hard-won compromise, a truce between gravity and matter after the more familiar forms of support have already failed. It is what remains when a star can no longer keep itself inflated by the ordinary outward push of heat from fusion, but still manages to avoid complete collapse. In that sense, a white dwarf is not merely a stellar remnant. It is a battlefield where collapse has been slowed, halted, and for a very long time held in check by one of the strangest forms of pressure in the universe. To understand why that matters, it helps to picture the life of an ordinary star in broad strokes. A star spends most of its existence balancing two competing tendencies. Gravity is always trying to pull its matter inward. Heat and pressure from the fusion reactions in the core are always pushing outward. As long as those two influences remain roughly balanced, the star survives in a fairly steady form. It shines, it radiates light and heat, it burns its nuclear fuel at a pace determined by its mass. From the outside, this can look wonderfully calm, though the interior is in fact an ongoing contest being conducted at temperatures and densities that would make calm seem a rather optimistic word. Eventually, though, the fuel runs low, not all at once, and not with some ceremonial dimming of the lights, but progressively. The core composition changes. The balance becomes harder to maintain. The star can no longer get the same outward support from the same fusion processes. Gravity, which has never once taken a day off, starts to gain ground. The core contracts, outer layers may expand, the star enters its later stages, and when stars of modest mass reach the end of that story, they do not explode into black holes or crush themselves immediately into something impossibly compact. They shed their outer layers and leave behind a hot, dense core. That core is the white dwarf. There is something almost austere about this final object. A white dwarf is no longer a star in the active, energetic, life-giving sense. It is not steadily fusing hydrogen in a luminous struggle against gravity. It is a stellar cinder, a remnant, a compact sphere of matter left behind after the brighter chapters are over. And yet, physically speaking, it may be more interesting than the star that created it, because the ordinary explanations have mostly run out. What keeps a white dwarf from collapsing further is not the usual thermal pressure of a star like the Sun. It is electron degeneracy pressure. That deeper quantum resistance we began approaching a moment ago is now the main line of defense. This changes everything about how the object behaves. A white dwarf is small compared with the star that made it, often about the size of Earth, yet it carries a mass comparable to that of a star. That alone is enough to make the imagination sit up a little straighter. Here is an object no larger than a planet, but with the mass of a sun-like star concentrated into that tiny volume. The result is a density so extreme that ordinary matter analogies begin to lose their usefulness. If you tried to compare white dwarf matter to steel or rock, or even the densest earthly substance you could think of, the comparison would not merely be inadequate, it would sound faintly embarrassed. But density is only part of the story. The real wonder is why the collapse stops at all. After all, the star has already lost the support of ongoing fusion. Gravity is still pulling inward with enormous force. Why does the remnant not simply keep shrinking? The answer is that the electrons in this matter have been packed into such close quarters that quantum mechanics refuses to let them all crowd into the same low-energy arrangements. The electrons are forced into a densely stacked set of states, and that stacking creates a pressure independent in the ordinary sense from keeping the whole object hot. The white dwarf pushes back because the electrons have run out of easy ways to be arranged. This means that the white dwarf is supported by something much less intuitive than a furnace. It is supported by a rule about what electrons are allowed to do. That may sound a bit dry on paper, but in cosmic terms it is astonishingly dramatic. A rule from quantum physics, formulated to describe the microscopic behavior of particles, ends up determining the fate of an entire star remnant. This is one of the great habits of the universe. It keeps taking laws that seem tiny and local, and using them to sculpt objects on a grand scale. If you like, you can think of a white dwarf as a star that has stopped burning, but has not stopped resisting. It no longer glows because it is generating new energy in the core at the old rate. It glows because it is still hot from its past and cools only slowly. But the support against gravity comes from the packed electrons themselves. It is as though the object has traded one kind of struggle for another. In its youth, it resisted gravity with heat and fusion. In its old age, it resists gravity with quantum crowding. That makes the phrase battle against collapse especially apt. A white dwarf is not in a relaxed state in the everyday sense. It is stable, yes, but stable in the way a carefully balanced arch is stable. Every part of the object is under enormous inward pull. Every layer contributes to the squeeze. The matter has nowhere to go except into a tighter and tighter arrangement, and only the electron degeneracy pressure prevents that arrangement from tightening without limit. The whole object is a held breath in stellar form. The more one thinks about it, the stranger the geometry of the situation becomes. Add mass to an ordinary object and we expect it to become larger if composition stays broadly the same. Add more dough and you get a bigger loaf. Add more water and the container fills higher. Add more books and the shelf problem becomes someone else's concern. But white dwarfs do not play by that friendly rule. Add more mass to a white dwarf and gravity becomes stronger. The inward squeeze intensifies. The electrons are forced into more extreme crowding. The degeneracy pressure rises to answer, but the overall result is that the white dwarf becomes smaller, not larger. More mass means a tighter object. This is one of the most elegant and unsettling features of white dwarfs. The very weight added to the star remnant makes it more compact. The object holds itself up by becoming denser. It is a balance, yes, but not a comfortable one. Every additional bit of mass increases the seriousness of the situation. The star remnant can survive it only by compressing further and relying more completely on the quantum nature of its electrons. This is also why there is a limit to how much mass a white dwarf can carry. Electron degeneracy pressure is powerful, but not infinite. There comes a point where the inward pull of gravity becomes too strong for this particular form of support to hold. This upper mass limit is one of the great turning points in astrophysics, because it decides whether a stellar remnant can remain a white dwarf or must collapse further into something even more severe. If a star leaves behind a core below that threshold, a white dwarf can form and persist. If the remnant is too massive, or if it gains more mass later, the battle changes character. Before we come to that, it is worth staying inside the white dwarf a little longer, because its interior is such an extraordinary place. The matter there is no longer ordinary atomic matter in the familiar sense. The nuclei are packed together in a dense arrangement with a sea of electrons providing the degeneracy pressure. Chemistry, in the way we usually think about it, has very little authority. There are no teapots, no crystals in the decorative sense, no polite little molecules continuing their surface world routines under difficult circumstances. The matter has crossed into a different regime. It is matter stripped down to something more severe and more fundamental. Even so, white dwarfs are not all identical. Their composition depends on the life history of the star that produced them. Many are expected to be made largely of carbon and oxygen in the core, the ash of earlier fusion stages. More massive progenitor stars may leave remnants with heavier compositions, but the central drama remains the same. Whatever the nuclei involved, the support comes from the electrons. The nature of the dense matter changes in detail, but the essential balance between gravity and electron degeneracy remains. There is also the question of heat, which gives white dwarfs a rather haunting quality. They are born hot, very hot. After all, they are the exposed remnants of stellar cores. But without ongoing fusion to maintain that heat, they cool with time. They radiate their stored thermal energy into space and gradually fade. This takes an immensely long time. A white dwarf can remain hot and luminous for billions of years, cooling slowly like a banked ember in the dark. There is something very calm about that image. A once brilliant star reduced to a compact glowing core, not dead in the sense of absolute coldness, but no longer alive in the old stellar sense either, just slowly, steadily, losing heat to the universe. And here again, white dwarfs reveal how different their internal support is from that of ordinary stars. As a normal star cools or loses the ability to generate heat, its structure changes dramatically because thermal pressure matters so much. A white dwarf can cool without collapsing immediately, because its support is not mainly thermal. The degeneracy pressure remains. The object fades, but the essential resistance stays in place. It is an old age sustained not by fresh energy, but by a deep rule of quantum structure. There is a quiet sort of humour in this if you are willing to grant the universe a dry wit. A star can spend millions or billions of years behaving like a radiant furnace, all heat and fusion and luminous ambition, only to end up supported by the stubborn refusal of electrons to share the same arrangements. One imagines gravity finding this deeply irritating. After all that patient inward pulling, to be thwarted by bookkeeping rules at the quantum level must feel, from gravity's point of view, like a technicality. Unfortunately for gravity, technicalities are sometimes the whole game. White dwarfs are also important because they do not always remain isolated and undisturbed. In binary systems, where two stars orbit one another, a white dwarf can interact with a companion. If matter from the companion star falls onto the white dwarf, the remnant may slowly gain mass. This can lead to fireworks of several kinds, some gentle by cosmic standards, and some rather less so. Material accumulating on the surface can ignite in bursts, producing novae. More dramatically, if the white dwarf approaches its maximum supported mass, the balance against collapse can fail catastrophically. In some cases, the result is a thermonuclear supernova, one of the most useful kinds of cosmic explosion for measuring vast distances across the universe. That is another remarkable feature of white dwarfs. Though they are stellar remnants, they are not always the end of the story. Under the wrong, or perhaps from a cosmic storyteller's point of view, the right conditions, they can become unstable in ways that matter enormously to the wider universe. A compact, quiet remnant can become the trigger for an explosion bright enough to outshine entire galaxies for a time. Even in old age, stars can remain surprisingly dramatic. Still, the most philosophically satisfying aspect of white dwarfs may be how clearly they reveal the layered nature of physical support. Matter does not resist collapse in one way only. First, there is ordinary material strength, which is enough for tables, mountains, and planets of modest scale. Then there is thermal pressure, which can hold up a shining star for a long while. When that is exhausted, there is electron degeneracy pressure. Each level belongs to a deeper or more extreme regime. White dwarfs sit precisely at the point where the universe says that ordinary atomic life is over, but one more layer of resistance still remains. This is why they feel like threshold objects. They are not ordinary stars, but neither are they yet the even darker compact remnants that come later. They are the first clear sign that matter, when pressed hard enough, abandons the familiar and survives by invoking more fundamental rules. The atom has already surrendered its everyday identity. Now the electrons are holding the line. The object remains, but it remains in a new language. There is also something rather moving in the fact that these remnants are so common. Most stars in the universe are not massive enough to end as neutron stars or black holes. Many will finish as white dwarfs. In that sense, the white dwarf is not an exotic exception, but a common conclusion. The future of a star like our Sun is not a spectacular collapse into a black hole, nor a final explosive passage into a neutron star, but a gentler, denser afterlife as a cooling white dwarf. The night sky of the far future will contain vast numbers of these compact fading relics, each one a testimony to a star that once shone more brightly. And yet the gentleness is only relative. A white dwarf may be quieter than a supernova, but there is nothing mild about the physics inside it. Gravity has crushed the matter to staggering density. The electrons are packed into an extreme quantum state. The surface gravity is immense. The whole object is balanced on the outcome of a relentless inward pressure and a deeply non-classical outward resistance. If you are somehow near its surface, which I do not recommend as a holiday plan, the environment would be profoundly hostile. The white dwarf may look serene from afar, but serenity and kindness are not the same thing. What keeps drawing people back to white dwarfs, I think, is that they embody a very pure form of physical necessity. Nothing about them is decorative. Every property matters. Their size, mass, density, cooling, stability, and possible failure all flow from a small set of principles pushed into an extreme regime. There is very little fluff, metaphorically speaking, though literally there was once quite a lot of stellar fluff before the outer layers drifted away. A white dwarf is the stripped-down result of gravity asking matter how little room it can survive with, and matter answering through the crowded defiance of electrons. Of course, that answer is not the final one. However strong electron degeneracy pressure may be, the universe can arrange situations where it is not enough. A white dwarf close to its mass limit exists in a precarious condition. Add too much more mass, or push conditions too far, and the balance gives way. The electrons can no longer prevent a deeper collapse, At that point, the old compromise fails, and a harsher negotiation begins. Electrons are pushed into protons. New particles become central. A new kind of star remnant appears, smaller, denser, and supported by an even more severe form of matter. So white dwarfs stand at a very particular place in the long ladder of compression. They are the objects that prove collapse can be halted after ordinary stellar life ends. They show how quantum mechanics can hold gravity at bay. They reveal the hidden strength of degenerate matter in one of its first great cosmic roles. But they also mark a limit. Beyond them waits a regime where the pressure is stronger, the matter stranger, and the battle against gravity fought on even narrower terms. When electron degeneracy pressure can no longer hold the line, the universe does not immediately give up and drop the whole affair straight into a black hole. That would be tidy in one sense, but nature is rarely in such a hurry. Instead, there is another stage of resistance waiting below the white dwarf, one more severe, more compact, and much less forgiving. If a collapsing stellar core is massive enough that the old compromise fails, gravity drives matter inward until the electrons themselves are forced into a new arrangement. They do not simply crowd harder and harder forever. Under extreme pressure, they are pushed into protons. The distinction between the old atomic ingredients begins to collapse. Electrons and protons combine, and neutrons take over the story. What remains is no longer a white dwarf, no longer ordinary plasma, and certainly no longer anything that resembles the material world of surfaces and chemistry. What remains is a neutron star. This is one of those names in astronomy that sounds almost modest considering the object it describes. Neutron star. It has a clean, practical ring to it, as though it might be a useful item in a well-organized drawer. In reality, a neutron star is one of the most extreme objects the universe routinely produces. It is the crushed core of a once massive star, packed so densely that a stellar mass fits inside something roughly the size of a city. Not continent, not a planet, a city. That contrast alone is enough to unsettle the imagination. A star's worth of matter, or a good fraction of one, compressed into a sphere so small you could place it comfortably within the distance of a morning commute, traffic permitting. To see how such an object forms, it helps to stay with the moment where the white dwarf style of support fails. In a sufficiently massive star, the core evolves through heavier and heavier stages of nuclear burning. Each phase produces ash that becomes fuel for the next, until the core is left with material that no longer yields energy by ordinary fusion in a helpful way. Gravity keeps pressing inward. The core contracts, temperatures rise, new reactions may occur for a while, but eventually the sequence runs out of useful options. At that point, the star is a serious problem. Fusion is no longer providing the outward support needed to counter gravity, and electron degeneracy pressure is not enough to hold up so much mass. Collapse begins in earnest. Once that collapse starts, it is swift and brutal. The core falls inward under its own weight. Densities soar. Electrons are squeezed into protons, producing neutrons and releasing floods of neutrinos. This process is sometimes called neutronization, and it marks one of the great turning points in the physics of matter. The particles that once built atoms, molecules, and the visible structures of ordinary matter are reorganized under pressure into something much simpler and more severe. The result is matter dominated by neutrons. The star's core has found a new way to pack itself tighter. This is not a gentle transition. It occurs in the violent context of core collapse, often associated with a supernova explosion that blasts the outer layers of the star into space. The explosion is one of the great spectacles of the cosmos, but for our purposes the more interesting part is what survives in the center. The remnant core, if its mass falls within the right range, does not keep collapsing without limit. Just as a white dwarf was halted by electron degeneracy pressure, the neutron star is halted by a deeper layer of resistance. Neutrons, like electrons, are fermions. They too obey the exclusion principle. they too cannot all collapse into the same identical state. Under enough compression, neutron degeneracy pressure and the strong interactions between the particles provide the support that resists further collapse. The star remnant stabilizes again, but at a far more extreme level than before. There is something almost severe in the logic of this progression. First, ordinary material structure resists, then thermal pressure in a normal star, then electron degeneracy in a white dwarf. Then, if the mass is greater still, neutrons become the basis of support. It is as though the universe is stripping matter down layer by layer, asking at each stage whether there is any deeper principle left to push back. Neutron stars are what you get when the answer is yes, but only just. The phrase edge of compression feels especially right here because neutron stars sit very close to a boundary. They are not the ultimate final state for all mass. Push the remnant still further and even neutron matter may fail to resist. But before that happens, neutron stars show us how astonishingly far matter can be compressed while still remaining, in some meaningful sense, matter rather than a black hole. They are the last stable stop on a narrowing road, the final place where a compact object can still have a surface, a crust, a magnetic field, and a personality of sorts before gravity becomes truly merciless. And neutron stars do have personalities in the astrophysical sense. Their masses, rotation rates, magnetic fields, temperatures, and surface conditions vary. Some spin calmly, some spin at absurd rates, hundreds of times each second, turning like cosmic kitchen appliances designed by someone with a deeply competitive streak. Some beam radiation from their magnetic poles and appear to pulse as they rotate, giving rise to pulsars. Some live in binary systems and accrete matter from companions. Some merge with one another in collisions so energetic they shake space and time itself in measurable ways. But beneath all this variety lies the same basic fact. A neutron star is matter compressed almost to the limit of what stable matter seems willing to bear. It is worth pausing on the density, because it is one of the few ways the mind begins to grasp how severe these objects are. A neutron star packs roughly stellar mass into a sphere only tens of kilometers across. That means the matter is unimaginably dense by everyday standards. The atoms are gone as atoms. Electron clouds are gone in any ordinary sense. The nuclei that once sat far apart in ordinary matter have been crushed into intimate contact. In much of the interior, it is as though one vast nucleus has taken the place of countless separate atomic nuclei, though even that picture is a simplification. The material is more like an ultra-dense sea of neutrons with a smaller admixture of other particles depending on depth and conditions. This is where language starts to become a bit strained. We can say the star is made of neutrons, and that is broadly true, but the detailed physics is more complicated. Near the surface there may be a crust where nuclei still exist in compressed arrangements, embedded in a sea of electrons. Deeper down, nuclei become more distorted, then begin to dissolve into a more continuous neutron-rich phase. Somewhere in that transition, theorists speak of exotic structures sometimes nicknamed nuclear pasta, because under certain conditions matter may form shapes resembling sheets, rods, or tangled layers. It is one of the rare moments in extreme astrophysics where the terminology sounds as though someone had become slightly hungry during a long calculation. But the point is serious. Matter under such pressure does not simply become uniform at once. It passes through dense and unusual arrangements on the way inward. Go deeper still, and the uncertainties grow. We think the interior is dominated by neutrons, but there may also be protons, electrons, muons, or even more exotic states depending on density. Some theories suggest that the innermost core of a neutron star might contain matter in which the neutrons themselves begin to lose their individuality, perhaps giving way to quark-rich phases or other unfamiliar arrangements. This is one reason neutron stars are so scientifically valuable. They are not just dense objects. They are laboratories where the behavior of matter under extreme compression can be tested in ways impossible on Earth. Each neutron star carries inside it a problem in nuclear physics, quantum theory, and gravity, all pressed into one very small sphere. And then there is the gravity. Surface gravity on a neutron star is immense. The escape speed is a significant fraction of the speed of light. Time itself runs a little differently near the surface because of the strong gravitational field. Like climbing away loses energy. The star's gravity bends the paths of radiation. The object is not a black hole, but it is close enough to serious gravity that ordinary intuitions about surface conditions need to be handled with care. If a white dwarf already represented a severe environment, a neutron star is that severity made much more concentrated. The crust of a neutron star, thin by stellar standards, is itself a remarkable thing. It is solid, but not solid in any household sense. It is thought to be among the strongest material structures in the universe, not because it was built from some superior metal alloy in a cosmic workshop, but because the matter is packed so tightly and held under such conditions that deforming it takes extraordinary stress. The crust can crack, however, and when it does, the result is sometimes described as a starquake. The name is sensible enough. A neutron star can undergo shifts in its crust or magnetic configuration, releasing energy in ways that can be detected across vast distances. Imagine an earthquake, strip out the tectonic plates, compress the whole object to city size, increase the gravity absurdly, add a magnetic field strong enough to make laboratory magnets look faintly decorative, and you're beginning to approach the idea. The magnetic fields deserve their own moment because some neutron stars carry magnetic fields of astonishing strength. In magnetars, the magnetic field becomes one of the defining features of the object, storing and releasing energy in violent outbursts. The field can influence the crust, the surface emission, and the surrounding environment. It is yet another reminder that neutron stars are not merely compressed balls of neutral matter sitting quietly in the dark. They are dynamic, extreme, and in some cases dramatically unstable in very particular ways. Even after surviving the collapse of a massive star, they continue to find new methods of being astrophysically inconvenient. Rotation also becomes important because when a stellar core collapses from a large object into a tiny one, it spins up. This is the familiar principle of conservation of angular momentum, though in this context it produces something far less familiar than a skater pulling in their arms. A neutron star can rotate very rapidly indeed. Pulsars, which emit beams of radiation from their magnetic poles, appear to flash as the beam sweeps across Earth. The regularity of some pulsars is extraordinary, so precise that for a time they were briefly considered possible signs of intelligent origin before astrophysics, with a certain lack of drama, explained them as rapidly spinning neutron stars. There is a lesson in that. If you ever detect a cosmic signal of almost unbelievable precision, it may not be aliens. It may simply be a dead star rotating with unreasonable discipline. All of this makes neutron stars rich objects of study, but the central issue for us remains compression. What matters most is the fact that neutron stars represent a state in which matter has been squeezed beyond the white dwarf stage and is now supported by neutron-based degeneracy and strong nuclear effects. The old atomic world is long gone. The electron-based support has been overwhelmed. The matter has been driven into a new regime where neutrons dominate. This is already about as far as stable matter seems willing to go under known conditions without disappearing behind an event horizon. That is why neutron stars sit at the edge, not merely because they are dense, but because they are precarious in a deeper conceptual sense. They occupy a narrow range of possibility. Too little mass, and you would not have formed one. Too much mass, and they cannot survive as neutron stars either. There is a maximum mass beyond which even neutron degeneracy pressure and nuclear repulsion can no longer support the object. The exact value depends on the poorly known details of the equation of state of ultradense matter, which is physicist language for how this exotic stuff responds to pressure and density. But the broad truth is clear. Neutron stars are not indefinitely scalable. Gravity can, in principle, win even here. This is one of the reasons neutron star mergers are so fascinating. When two neutron stars spiral together and collide, the combined object may briefly form a more massive remnant before collapsing further, or it may collapse promptly depending on the total mass and the details of the matter inside. These mergers produce gravitational waves, bursts of radiation, and the conditions needed for creating some of the heavy elements in the universe. Gold, platinum, and other heavy elements owe part of their cosmic abundance to events like these. So the edge of compression is not only a story about limits, it is also a story about creation. The extreme physics of compact objects helps seed the universe with material that later becomes planets, jewelry, electronics, and the occasional regrettable purchase. Still, neutron stars are not romantic objects in the usual sense. They are too severe for that. What they offer instead is a sort of physical honesty. They show what matter does when there is almost no room left. They show how far gravity can push before stable structure gives out entirely. They show that nature has more than one fallback plan when ordinary conditions fail, but also that each fallback plan has a boundary. The neutron star is perhaps the clearest example of matter surviving under almost impossible conditions by becoming something more stripped down and more densely organised than anything in the familiar world. It is also worth noting that in a neutron star, the distinction between matter and gravity begins to feel much tighter than before. In a planet, gravity shapes the interior, but the object still feels comfortably like an object. In a white dwarf, gravity and quantum pressure are locked in a serious contest. In a neutron star, the contest has become so intense that the geometry of space and time around the object is part of the story in a very noticeable way. The object is still matter with a surface, yes, but it lives in such strong gravity that general relativity is no longer a polite correction. It is part of the main event. This is important because the closer we come to the limits of compression, the less we can separate the questions cleanly. What can matter endure? What pressure can it support? How strongly does gravity curve the surrounding space-time? At ordinary scales, these can feel like separate subjects. In neutron stars, they begin to merge. The star's internal structure depends on gravity. Gravity depends on the star's mass and compactness. The pressure support depends on the behaviour of matter under those conditions. Everything feeds back into everything else. The neutron star is a problem where quantum rules, nuclear interactions, and relativity all meet in one stubbornly small object, and yet even neutron stars do not answer the question all the way. They show us the most extreme stable matter we know with confidence, but they do not tell us what happens at the absolute end of compression. They show a boundary, not the final principle beyond it. If you ask how much pressure matter can take, the neutron star gives you one of the sternest answers in nature, but not the ultimate one. It says matter can endure enough pressure to erase atoms, overwhelm electron support, and force matter into neutron-rich ultra-dense forms. It says matter can survive in a state so compact that an entire star fits within city-scale dimensions. It says gravity can be resisted at levels far beyond planets and white dwarfs. But it also says there is a final narrowing ahead. Because somewhere beyond the neutron star, beyond even the uncertain inner core where exotic dense matter may lurk, lies a deeper question. Not merely what state matter enters next, but whether our whole framework for pressure, particles and space-time remains adequate. Neutron stars live close enough to that boundary to make it visible. They are not yet the breakdown of physics, but they point toward it. They are the last clear signpost before the road becomes speculative, where the language of known matter starts to thin and the idea of an ultimate pressure limit begins to matter in earnest. By the time we reach this point, the question has changed shape more than once. At first it sounded almost practical. How much pressure can matter take? That feels like something you might ask in a workshop, a laboratory, or while looking at a machine that has begun making sounds no machine should ever make if it wishes to inspire confidence. Then the question widened. We followed pressure through the interiors of planets, into stars, into the wreckage of stars, and finally into neutron stars, where matter is compressed so brutally that atoms are long gone, and the particles left behind are packed into one of the densest stable forms nature seems willing to allow. That already feels extreme enough. It already feels like the sort of answer that ought to satisfy a reasonable person. But physics is not always interested in what satisfies a reasonable person. Physics asks the next question. If neutron stars bring us close to the edge, where is the edge itself? Is there a final pressure, not just for rock or iron or atoms or neutron-rich matter, but for physics as we currently understand it? That is where Planck pressure enters the story. The first thing to say about Planck pressure is that it is not the pressure inside some particularly impressive object. It is not the pressure at the centre of an exotic planet, or the pressure inside a neutron star, or even the pressure in a collapsing star just before things become dramatic. It is a theoretical scale, a limit built from the deepest constants we know, a point where the separate pillars of modern physics begin to stop feeling separate. When physicists attach the word Planck to something, they are usually pointing toward a natural boundary, a scale at which gravity, quantum theory, and relativity can no longer be discussed as though each were taking care of its own department in a well-run institution. At a Planck scale, all of them matter at once. That is what makes this pressure different from every other kind we have talked about so far. Pressure inside a planet can be estimated using gravity and material response. Pressure inside a normal star can be described using thermal motion, radiation, and gravity. Pressure inside a white dwarf or neutron star requires quantum mechanics and dense matter physics. But Planck pressure sits beyond even those. It represents a regime where our present theories, powerful though they are, begin to look incomplete. Not wrong in the everyday sense, but unfinished. They stop fitting together cleanly. This is worth lingering over because it is easy to hear the phrase ultimate limit and imagine a simple physical barrier, like the maximum weight a bridge can hold or the highest pressure a container can withstand before it fails in a noisy and regrettable manner. Planck pressure is not quite like that. It is not a certified safety rating for matter. It is not a number stamped on the side of the universe with a helpful note from the manufacturer. It is more like a warning sign that appears when you push known physics to the point where the ordinary distinction between matter, energy, space, and gravity begins to blur. At that scale, pressure is no longer just something matter experiences. It is something so intense that the very stage on which matter exists may no longer behave in the familiar way. To understand why, it helps to back up and talk about what the Planck scale really means. Max Planck, early in the history of quantum theory, noticed that certain combinations of fundamental constants could be used to define natural units, not meters chosen by human convention or seconds originally tied to the turning of Earth, but scales that seem to come from the universe itself. If you take the constant that sets the strength of quantum effects, the constant that sets the speed of light, and the constant that governs gravity, and combine them in the right way, you get natural measures of length, time, mass, energy, and other quantities. These are not ordinary scales. They are incredibly extreme, and they are interesting because they mark the point where none of the major frameworks can be ignored. At everyday scales, gravity is usually weak enough that quantum mechanics can be handled without worrying much about the curvature of space and time. At the scale of planets and stars, gravity matters enormously, but quantum effects can often be reserved for special situations. At the scale of atoms, quantum mechanics dominates, while gravity is so feeble it might as well be in the next room making tea. But at the Planck scale, the separation breaks down. Quantum theory matters, gravity matters, relativity matters. Everything matters at once, which is very satisfying philosophically and very inconvenient mathematically. Planck pressure is the pressure scale associated with that regime. It is so vast that calling it enormous does not really help. Every pressure we have discussed before this point, from the deep interiors of planets to the centres of compact stars, is still modest compared with it. Not modest in any ordinary sense, of course. A neutron star is not a modest object unless one is comparing it to a black hole while feeling unusually casual. But Planck pressure is beyond those known astrophysical environments. It is not the next step after neutron stars in the sense that you just squeeze a little harder and there you are. It is a far deeper boundary. A theoretical frontier where our language of matter under pressure may cease to be adequate. One useful way to think about pressure at these extremes is to connect it with energy density. Pressure and energy density are closely related in high-energy physics and cosmology. The more energy you try to confine into a given region, the more severe the effective pressure becomes. In ordinary systems, this is just one perspective among many. In extreme systems, it becomes increasingly central. Planck pressure therefore corresponds to an energy density so immense that space and time themselves cannot be treated as a smooth passive background. The energy is not merely in space, it becomes a problem for the structure of space. That is the real shift in meaning. Up to a point when matter is compressed, we can talk about particles, phases, equations of state, degeneracy pressure, nuclear interactions, and gravitational balance. The matter is exotic, but it is still describable as matter occupying a region within space-time. Near the Planck pressure, that way of speaking becomes questionable. If quantum fluctuations of the gravitational field become unavoidable, if space-time itself no longer behaves like a calm continuous arena, then what exactly is doing the pressing and what exactly is being pressed are no longer straightforward questions. This is why the phrase ultimate limit is more about theory than about material toughness. There is no known stable chunk of matter sitting somewhere in the cosmos, calmly tolerating Planck pressure while getting on with its evening. In fact, our best understanding suggests that trying to force so much energy into so small a region would likely lead to gravitational collapse of one kind or another, long before you could describe the system as some tidy hypercompressed material sample. The issue is not that matter becomes super strong and then eventually gives up at a final number. The issue is that the entire framework of matter in a background space-time may stop being the right description. This is where black holes naturally enter the conversation, because black holes are what happen when gravity wins so completely that an event horizon forms. Yet even black holes do not simply hand us Planck pressure in a neat, usable form. Outside the event horizon, a black hole can be described rather elegantly by relativity. The trouble lies in what classical theory predicts deep inside. There, under the old equations, matter is driven toward a singularity, a place where density and curvature formally diverge and the mathematics loses its composure entirely. Most physicists take this not as evidence that nature truly contains such an unmanageable point in the literal classical sense, but as a sign that the theory has reached beyond its domain of trust. Something new is needed. Some theory of quantum gravity must take over, and the Planck scale is the place where we expect that takeover to become unavoidable. In other words, Planck pressure is tied to the same kind of warning we see in black hole singularities and in our attempts to describe the earliest moments of the universe. It is the pressure scale at which current theory points toward its own incompleteness. That is a fascinating kind of limit. It is not simply the last pressure matter can bear before failing. It is the last pressure at which our present categories are likely to remain meaningful. There is something wonderfully humbling about that. Humans are very good at extending familiar ideas upward. We see a table hold a book, then a beam hold a roof, then rock support a mountain, then pressure shape a planet, then degeneracy support a star remnant, and we are tempted to imagine a continuous ladder. Just keep climbing. Keep increasing the pressure, keep finding stronger kinds of matter, but Planck pressure tells us the ladder may not continue in that simple way. At some point, the question itself becomes unstable, not because curiosity has failed, but because the world is more structurally complicated than our intuitions allow. It is also useful to be careful about what Planck pressure does not mean. It does not mean that matter has a single universal breaking point in the ordinary engineering sense. Different forms of matter fail transform or reorganize under very different conditions. A solid cracks, a gas compresses, atoms ionize, electron degeneracy appears. Neutron-rich matter forms. Each stage belongs to a different regime. Planck pressure is not one more material phase after neutron stars in the way liquid water is one more phase after ice. It is a scale where the distinction between phases of matter may itself become secondary to deeper questions about space-time and quantum geometry. That phrase, quantum geometry, is worth taking slowly, because it hints at what many physicists suspect lies beyond our present picture. In general relativity, gravity is the curvature of space-time. In quantum physics, particles and fields are described by probabilistic rules and discrete interactions. These two frameworks are both enormously successful in their own domains, but they do not fit together cleanly at the Planck scale. So when we speak about the ultimate pressure, we are really speaking about the pressure at which a unified description would become necessary. Perhaps space-time has a discrete structure at that scale. Perhaps what we call space is emergent from something deeper. Perhaps black hole interiors or the early universe are governed by rules we have only partially guessed at. Planck pressure sits at that doorway. This is why it appears in cosmology as much as in discussions of collapse. The very early universe, near the beginning of its expansion, likely reached densities and pressures approaching the Planck regime. There too, our familiar theories stop short. We can describe a great deal about the early hot universe after a certain point, but not the absolute beginning with full confidence. Once again, the issue is not that nothing can be said, but that the known frameworks run into one another too violently. The pressure scale there is telling us the same thing as the most extreme collapse scenarios. Past this point you need a deeper theory. There is a certain economy to that. The largest questions and the smallest scales meeting in the same place. The interior of a black hole, the earliest instant of cosmic history, and the idea of ultimate compression all pointing toward the same unresolved boundary. That is not a sign of confusion so much as a sign that there is one deeper problem hiding beneath several apparently different ones. Still, one might reasonably ask whether Planck pressure is physically real if we cannot yet describe the regime properly. The answer, in the scientific sense, is yes as a natural scale, and no as a fully understood state of matter. It is real in the sense that the constants of nature define it. It is meaningful in the sense that it marks where our theories should be expected to fail if pushed too far. But it is not real in the sense that we have a tested, complete model of what matter or space-time actually does there. We have the threshold more clearly than the territory beyond it. This distinction matters because it keeps us honest. Physics is at its best when it knows where it is confident and where it is guessing carefully. We can estimate the Planck scale, we can say why it matters. We can explain why pressures that high imply a breakdown of the clean divide between quantum theory and gravity. We cannot yet tell a fully settled story of what compressed reality becomes there. That is part of the beauty of the topic. The limit is not just an answer, it is also an open question. And perhaps that is the most surprising turn in the whole story. We began by asking how much pressure matter can take, expecting perhaps a mighty number or a dramatic state of ultra-compressed substance. Instead, the deepest answer leads us to a place where matter may no longer be the only thing in the conversation. The question spills over into the nature of space, time, energy, and law itself. Pressure at the ultimate scale is not just about squeezing particles. It is about whether the arena of existence remains smooth enough for particles to be the right language. If there is a mild joke hiding in all this, it is that after all our effort to find the strongest possible form of matter, the universe responds by saying that the problem is no longer really about matter in the way you meant. One can almost hear physics clearing its throat and pointing toward a much larger chalkboard. That does not make the journey disappointing. Quite the opposite. It means the search has been successful enough to uncover its own boundary. We now know that planets are pressure-shaped worlds, that atoms surrender under sufficient compression, that white dwarfs are held up by electron degeneracy, that neutron stars press matter to the edge of known stability, and that beyond those known structures lies a theoretical pressure scale where our present understanding is expected to fracture. That is an extraordinary amount to learn from one apparently simple question. And yet, knowing that the limit exists is not the same as understanding what lies there. The word ultimate can be misleading in that sense. It sounds final, conclusive, neatly wrapped. But Planck pressure is ultimate only as a marker of where the known road ends. It does not tell us what the new country looks like. It tells us only that the old map will not do. So when physicists invoke Planck pressure, they are really saying something both bold and cautious. Bold because they are pointing to the deepest regime implied by our constants of nature. Cautious because they are admitting that the tools we've used so effectively elsewhere are not enough on their own once we arrive there. It is one of the rare moments in science where a number becomes almost philosophical. Not because it is vague, but because it is too precise for the old language to survive around it, which leaves us standing in an interesting place. We have reached the pressure scale that signals the boundary of known theory, but that boundary is not a wall with a tidy label. It is more like the edge of firm ground where the surface starts to crack underfoot and the familiar landmarks disappear into fog. The next step is no longer about stronger planets or denser stars. It is about what happens when the rules that carried us this far begin to stop fitting together cleanly and physics itself starts to come apart at the seams. That fraying point is one of the strangest places in all of science, because when physicists say that physics begins to break apart, they do not mean that nature itself becomes confused or that the universe suddenly loses interest in being orderly. Nature, as far as we can tell, goes right on doing whatever it does with complete confidence. The part that breaks apart is our description. The theories that work so beautifully in their own proper ranges begin to pull against one another. Their assumptions stop fitting together neatly. Their language starts to sound slightly mismatched. It is a little like discovering that two maps of the same country are both excellent, until you reach the border where one was drawn for roads and the other for railways, and neither is especially helpful for crossing a swamp in the dark. Most of physics is built on that kind of division of labour. For ordinary objects, ordinary speeds and ordinary energies, classical ideas do wonderfully well. For atoms, molecules and subatomic particles, quantum mechanics takes over and gives astonishingly accurate answers. For gravity on large scales, for planets and stars and the shape of the universe, general relativity is one of the finest theories ever written down. Each of these frameworks is not merely useful, it is brilliant. The problem is that they were not built to answer every question at once. Each one comes with assumptions about what can be ignored. Most of the time, that is not a weakness at all. It is the reason the theories are usable. But under enough compression, at high enough densities and pressures, the things each theory likes to ignore can no longer be ignored. That is the basic difficulty. General relativity describes gravity as the curvature of space-time. Matter and energy tell space-time how to curve, and curved space-time tells matter how to move. It is an elegant picture, and it has passed every serious test thrown at it in its domain. But general relativity treats space-time as smooth and continuous. Quantum theory, on the other hand, is built around uncertainty, discrete states, probabilistic behaviour, and fields that do not always behave as calm, classical surfaces. It is equally elegant in its own way, though perhaps less likely to make you feel as though the universe has chosen the easy route. And when the pressures become extreme enough, both gravity and quantum effects become central at the same time. That is where the trouble begins in earnest. In ordinary laboratory conditions, gravity is so weak compared with other forces that quantum theory can proceed without worrying much about it. In most large-scale gravitational systems, quantum effects are too small to dominate the structure. But if you compress enough mass and energy into a small enough region, then the gravitational field becomes very strong while the relevant distances become very small. At that point, quantum mechanics and gravity are both essential, and the theories we have do not merge cleanly into a complete single framework. This is why the word break is appropriate. though it must be handled carefully. It is not that the equations start shouting at one another, or that a textbook bursts into flames when you open it to the wrong page. It is that the calculations begin producing infinities, or contradictions or situations where the assumptions behind the theory no longer make sense. One theory may tell you to treat space and time as a smooth stage. Another may tell you that uncertainty and quantum fluctuations cannot be ignored. Try to obey both at once in the deepest compression regimes, and the picture stops being trustworthy. Black holes provide the most famous example of this problem. According to general relativity, if enough mass collapses inward and no known pressure can halt it, an event horizon forms. Beyond that horizon, the collapse continues. Follow the classical equations all the way down and they lead to a singularity, a point where density becomes formally infinite and curvature becomes infinite as well. That word infinite is usually the clue that something has gone badly wrong in a physical theory. Not always, but often enough that physicists pay attention. Infinity, in a final prediction, is usually nature's way of telling us that the theory has been pushed beyond the circumstances where it deserves our trust. A singularity, then, is less a well-understood object than a sign of theoretical breakdown. It tells us that general relativity, magnificent though it is, cannot be the full story all the way down. Somewhere before that impossible point, something deeper must intervene. Perhaps space-time ceases to be smooth. Perhaps quantum effects alter the collapse. Perhaps there is no true point like the classical singularity at all, only a region where a better theory would describe a very different state of affairs. We do not yet know. What we do know is that the old picture becomes unreliable. The same warning appears when we think about the earliest moments of the universe. If we run cosmic expansion backward using general relativity, the universe becomes denser, hotter, and more compressed. Eventually, once again, the equations lead us toward a singular beginning. And once again, physicists are not inclined to treat this as a triumph of final understanding. It is another sign that something is missing. A complete description of the earliest universe would require the physics of quantum gravity, a theory that does not yet exist in a fully tested and settled form. That phrase, quantum gravity, is really the heart of the matter. It is the name we give to the missing framework, the still unfinished bridge between quantum mechanics and general relativity. We know such a bridge must exist because the world does not stop being one world when the pressures get high. The universe does not divide itself into a gravity department and a quantum department with separate office hours. If there are situations where both are essential, then there must be some more complete description that contains them both. The difficulty is finding it. One reason this has proved so hard is that quantum theory and general relativity do not merely describe different things, they organize reality differently. In ordinary quantum mechanics, time is usually treated as a given background parameter. Things evolve in time. Time itself sits there calmly in the equations like a reliable clock keeping track of events. In general relativity, time is not separate from the geometry. It can stretch, curve, and flow differently depending on gravity and motion. So even the role of time is treated differently by the two frameworks. That is not a small disagreement. It is a deep structural mismatch. Space suffers from a similar problem. In quantum field theory, fields are often described as living on a space-time background. In general relativity, space-time is not background. It is dynamic. It is part of the physics. So when the pressures become so severe that the energy density itself should strongly affect space-time at tiny scales, the old arrangement in which quantum fields politely sit on a fixed stage starts to look suspicious. The stage is wobbling. Perhaps it is not even a stage in the old sense anymore. This is why physicists sometimes talk about space-time foam or quantum fluctuations of geometry at extremely small scales. The idea is not that space literally turns into bath bubbles, though that would certainly make conference talks livelier. The point is that at sufficiently tiny scales and extreme conditions, Space-time may no longer be smooth and continuous in the way general relativity treats it. It may fluctuate. It may have a discrete structure. It may emerge from something more fundamental that does not look like ordinary space and time at all. These are not settled answers, but they are plausible directions because the old description no longer seems able to carry the full load. It is worth noticing how odd that is from the human point of view. We began with pressure as a familiar experience. A tire, a hand, a deep pool, a rock under strain. Now we have followed it so far that the thing being strained may be space-time itself. The concept has changed scale completely. At first, pressure was about matter resisting compression. Now it is about whether the arena in which matter exists remains the same sort of arena under ultimate compression. That is not merely an increase in quantity, it is a shift in category. String theory is one attempt to build the missing bridge. In that framework, the fundamental ingredients of nature are not point-like particles in the ordinary sense, but tiny extended objects whose different vibrational modes correspond to different particles. One of the appealing features of string theory is that gravity appears naturally within it. That made many physicists hopeful that it could provide a consistent quantum theory of gravity. It has produced deep mathematical insights and has influenced modern theoretical physics enormously. But it has not yet delivered the kind of decisive experimental confirmation that would settle the matter, so it remains a powerful and sophisticated candidate, not a final answer. Loop quantum gravity is another approach. Instead of replacing particles with strings, it tries to quantize space-time itself more directly. In this picture, space may have a granular or discrete structure at the tiniest scales. Area and volume might come in indivisible chunks, rather than varying continuously all the way down. Again, this is an effort to take seriously the idea that smooth space-time may break down at the deepest level. Again, there are elegant ideas and intriguing results. Again, there is no universally accepted final theory. There are other approaches too, and that alone tells us something important. When a scientific field produces many serious candidate frameworks, it often means the problem is profound, and the data are not yet sharp enough to settle the question cleanly. No one doubts that the current picture is incomplete in these extreme regimes. The uncertainty lies in what the replacement will look like. Meanwhile, black hole physics keeps sharpening the problem in ways that are both technical and oddly philosophical. One example is the information problem. Quantum theory is built in a way that strongly suggests information should not simply vanish from the universe without trace. But classical black holes, with their horizons and singularities, raise the unsettling possibility that information might be lost behind the horizon and effectively destroyed. Then came Hawking radiation, the idea that black holes are not entirely black but radiate due to quantum effects near the horizon. That deepened the puzzle. If a black hole can evaporate over time, what happens to the information about what fell in? Is it somehow encoded in the radiation? Is it trapped? Is the whole description of the horizon incomplete? Physicists have spent decades wrestling with this, and while there has been real progress, it remains one of the clearest signs that gravity, quantum theory, and our basic ideas about reality are still not fully reconciled. It is almost comical, in a dry and highly educated sort of way, that when we push the universe hard enough, we do not just get difficult numbers, we get questions about information, reality, geometry, and causality. The machinery of physics keeps running until suddenly it opens a side door into philosophy and waves us inside. Still, the issue is not abstract in the unhelpful sense. It is grounded in very concrete physical circumstances, a collapsing star core, the interior of a black hole, the earliest cosmic moments. These are not imaginary settings invented to make seminars more dramatic. They are real arenas where the known theories point toward their own incompleteness. We cannot yet visit them directly in the ordinary experimental way, but we can study their consequences, compare predictions, observe compact objects, detect gravitational waves, and test the limits of our frameworks from every angle available. Neutron stars in particular are interesting because they sit just short of the full breakdown. They are close enough to the edge that the uncertain physics of dense matter and strong gravity becomes impossible to ignore, yet they still remain accessible to observation in ways black hole interiors do not. Their masses, radii, mergers, cooling behaviour, and surface phenomena all give clues about how matter behaves near the boundary of known compression. In that sense, neutron stars are less the place where physics breaks apart and more the place where it begins to fray visibly. Once you cross beyond that into collapse regimes associated with black holes and Planck scale pressures, the fraying becomes more severe. We no longer trust the classical picture all the way inward. We no longer know whether space-time remains continuous. We no longer know whether the interior should be described in terms of particles, fields, geometry, or something more basic from which all of those emerge. It is as though the familiar ingredients of physics keep their names for a while, but stop behaving like the things those names used to describe. That makes this one of the most exciting frontiers in science, but also one of the easiest to speak about badly. It is very tempting to cover the uncertainty with grand language, mystical language, or tidy confident language. None of those are especially helpful. The honest position is both simpler and more interesting. We know where the known theories work. We know where they begin to conflict. We know roughly what scale marks the conflict becoming unavoidable. We do not yet know what the full replacement theory is. That is not a weakness of science. It is science being honest about the edge of its map. There is also a practical lesson in this. Theories are not sacred. They are tools of astonishing power, but they are still tools. Their greatness lies not in pretending to answer every question forever, but in answering the questions they can answer with extraordinary precision and in making clear where they fail. General relativity does not become a poor theory, because singularities signal its limit. Quantum mechanics does not become untrustworthy because it has not yet been reconciled with full dynamical space-time. Their very precision is what exposes the problem. Lesser theories would have blurred it. So when physics begins to break apart, what we are really watching is something rather noble. We are watching powerful human understanding reach the point where it can identify its own boundary. The equations do not go soft and vague. They go sharp enough to reveal the crack. And the crack appears exactly where the universe becomes most compressed, most curved, most extreme. Pressure brought us here. It drove planets into layers, atoms out of their comfort, white dwarfs into quantum support, neutron stars to the edge of stable compression, and finally led us to the place where matter, gravity, space, and time can no longer be treated as separate tidy subjects. That is why this breakdown matters. It is not a detour from the question of matter under pressure. It is the deepest form of that question. If you ask how much pressure matter can take, you eventually arrive at the point where the answer depends on what matter is, what space is, what time is, and whether those are the right categories at all. And yet, even here, there is one more step to take. Because once physics begins to break apart, the next question is not only what theory replaces it, but what the last meaningful threshold of matter really is before the old language gives way completely. So this is where the question becomes as narrow as it can be before it stops being the same question. We began with matter as something familiar, something you could hold, lean on, compress, hammer, stack, carve, crack, melt, weigh, or drop in a way that would be educational for a fraction of a second and then mostly regrettable. Then we followed pressure downward through larger and harsher arenas. We watched planets squeeze their interiors into denser forms. We watched atoms surrender their ordinary identities. We watched white dwarfs survive by the crowded discipline of electrons. We watched neutron stars push matter almost to the edge of what stable structure seems willing to allow. And after all of that, the final threshold of matter turns out not to be one neat border stone with a tidy label. It is the point where matter, as a distinct and useful concept, begins to blur into something deeper. That is perhaps the most important thing to say at the outset of this last stretch. The final threshold is not simply the moment matter breaks. It is the moment the old description of matter becomes too narrow to carry the full burden of what is happening. That is a subtle difference, but it matters. A glass breaks, and it is still glass, only in a less successful arrangement. A rock fractures and remains rock. Even atoms can surrender their usual form, and the system can still be described in terms of particles packed into new states. But somewhere beyond the last stable compression of neutron-rich matter, we reach conditions where the question is no longer just what state matter has entered. The question becomes whether matter can still be separated from the space-time in which it exists strongly enough for the word to keep its old meaning. This is a difficult place to picture because nearly all our instincts were trained on gentler circumstances. Matter, in daily life, is the thing. Space is where the thing is. Time is what happens while the thing does whatever it is doing. Gravity is the force or curvature that influences the thing. The categories feel clean, they feel natural. But under sufficient compression, those categories start leaning into one another so severely that they are no longer easy to isolate. Matter curves space-time. Curved space-time guides matter. Quantum rules shape the allowed states of particles. And at the deepest limit, the distinction between the stage and the actor begins to fade. That fading is the last threshold. One way to approach it is by asking what we really mean by matter in the first place. In ordinary terms, matter is whatever has mass, occupies space, and can be arranged into structures. Fine enough as a starting point. Atoms build molecules. Molecules build materials. Materials build planets, bodies, trees, clouds, spoons, and stars. Even when conditions become extreme, we tend to preserve that picture as long as possible. A white dwarf is matter in a dense state. A neutron star is matter in a denser and stranger state. So we keep going. We keep assuming that further compression will yield another state, and then perhaps another, as though the universe were a cabinet of increasingly difficult drawers. But the ladder may not continue in that simple way. At some point, the very ingredients of the description begin to resist being separated. If space-time becomes subject to quantum uncertainty, if geometry itself no longer behaves as a smooth background, then matter may no longer be the right first word. Perhaps there is some deeper entity from which both matter and space-time emerge. Perhaps what we call matter is only one stable behaviour of a more fundamental structure. If that is true, then the last threshold of matter is not a final phase of matter at all. It is the boundary where matter ceases to be the most basic, useful category. This is not an act of surrender by physics so much as an act of precision. Good theories tell you where their own vocabulary begins to strain. Up to a point we can speak about particles under pressure. Then we must speak about dense quantum states. Then about general relativity and strong gravity. Then, nearing the Planck scale, we begin to suspect that neither particles on a background nor geometry without quantum structure will do the job alone. The threshold is therefore not just extreme pressure, it is the edge of a language. That sounds abstract, but there are good physical reasons to say it this way. Consider what happens in an ordinary star when compression increases. Thermal pressure grows, the particles move more energetically. If fusion is available, the star may reach a stable balance. Fine. Consider a white dwarf. Compression is no longer mainly balanced by thermal motion, but by electron degeneracy. Fine again, though already rather more exotic. Consider a neutron star. Now even electrons have lost their old role, and the structure of matter is dominated by neutrons and the strong nuclear interaction under astonishing density. Still difficult, but still describable. Each time the matter survives by revealing a deeper mechanism of resistance. The natural hope is that there is always one more layer. Yet black holes warn us that there may not be an endlessly usable sequence of matter states. Once collapse passes beyond the point where known pressures can halt it, we do not obtain a tidy catalogue entry for the next type of substance. We obtain an event horizon, a region from which no signal escapes in the ordinary way, and within the classical description, the path leads toward a singularity. That singularity is not usually taken as a literal final object in the simple sense. It is a sign that the theory has gone beyond its proper jurisdiction. Still, what it tells us is profound. There may be conditions under which matter no longer survives as matter in the sense we have carried all along. It may be that collapse does not reveal a stronger material, but removes the usefulness of material description altogether. That possibility changes the flavour of the original question. How much pressure can matter take? One answer is that matter can take enough pressure to become plasma, enough to dissolve atoms, enough to become electron degenerate, enough to become neutron rich, enough to create some of the most extreme stable objects in the universe. Another answer is that beyond a certain point matter no longer takes pressure as matter. The system enters a regime where our best current frameworks point not to a more resilient substance, but to the breakdown of the categories themselves. There is something both frustrating and beautiful in that. Frustrating because it denies us the neatness of a final material answer. Beautiful because it suggests the universe is deeper than any one category we happen to build our understanding around. Matter feels fundamental because it is the most obvious stable thing in our experience. But perhaps it is not the final layer. Perhaps it is a long, lived and richly structured appearance within something more basic. Some physicists suspect that even space-time is emergent, that the smooth geometry we talk about in relativity might arise from underlying quantum relationships the way temperature arises from the collective motion of many particles. If that is true, then matter and space-time may both be secondary features of a deeper reality. Under everyday conditions, they separate cleanly enough to let us build science, technology, architecture, and very complicated coffee machines. Under ultimate compression, they may return to that deeper level, losing the distinctness that made them manageable. If so, the last threshold of matter is less like a wall and more like a melting point of conceptual identity. Not a melting point in the literal thermal sense, but a boundary where a familiar thing loses the stability of its definition. We have seen versions of this before at smaller scales. Water is not steam and not ice, yet all are the same substance under different conditions. Atoms in ordinary matter are not the same as pressure ionized matter, though the nuclei remain. A neutron star is not chemically familiar material, though it descends from ordinary stellar matter by compression. The lesson throughout has been that identity in physics is often conditional. The final threshold simply extends that lesson to the point where the condition may include the breakdown of matter itself as a standalone idea. There is another way to see this, and it comes from the relation between structure and information. Matter, in every regime we have discussed, carries structure. Atoms have arrangements, molecules have bonds, solids have lattices or amorphous forms, white dwarfs have electron-supported configurations, neutron stars have crusts, interiors, and equations of state. Structure means there are distinguishable patterns, and those patterns are part of what we mean by matter rather than featureless energy. But in the deepest collapse scenarios, information and structure become part of the puzzle in a much more severe way. Black hole thermodynamics and the information problem suggest that the last threshold of matter is inseparable from the last threshold of how physical information is stored and transformed. Matter is not merely stuff, it is organized stuff. If the organization becomes unreadable or inaccessible in the old language, then matter as a concept is already under strain. This is why black holes haunt the subject even when they do not hand us a clean answer. They represent the possibility that compression eventually wins so completely that surface, interior and material state no longer fit the old picture. From outside, a black hole can be described by a surprisingly small set of properties: mass, spin, charge if any. The rich details of the matter that fell in seem to disappear behind the horizon, at least in the simple classical view. That is a remarkable reduction. The universe starts with stars full of layered chemistry and plasma dynamics, and ends with an object that from afar seems almost minimal. It is as though compression has not merely squeezed matter, but simplified its outward identity to the barest terms. and yet even that simplification may conceal something deeper rather than erase it. Many modern ideas in theoretical physics suggest that information is not truly destroyed, only transformed in ways we do not yet fully understand. That means the final threshold of matter may not be annihilation, but translation into a form we cannot yet fluently read. The matter is not gone in the sense of meaninglessly lost. It is beyond the grammar of present theory. That thought has a certain quiet dignity to it. The universe may not discard structure so much as hide it inside a deeper accounting system. Our failure is not necessarily that the world becomes senseless, only that our best current language cannot follow it all the way in. Even if one avoids the black hole route and stays just short of full collapse, the same lesson lingers. The inner cores of neutron stars may already contain phases of matter that challenge our standard names. Hyperons may appear, quark-rich matter may emerge, condensates of unfamiliar sorts may become favourable. None of this is settled, but the trend is clear. As density rises, the material world becomes less like the one we know, and more like a hierarchy of increasingly stripped-down descriptions. First chemistry fades, then atomic identity fades, then nuclear individuality may begin to fade. The last threshold is simply the point at which there is no further familiar level to peel back without stepping outside the old conceptual frame entirely. There is an almost literary symmetry in that. We began with the ordinary world, where matter seems obvious and time seems steady and surfaces feel solid. We followed pressure into regions where each of those assumptions had to be revised. Time bent under gravity. Surfaces turned out to be electromagnetic resistance. Solids revealed atomic architecture. Atoms revealed quantum constraints. Stars revealed degeneracy. Neutron stars revealed the edge of stability. And now, at the final threshold, matter itself reveals that it may not be the final noun. If you like, you can think of the whole journey as a lesson in humility delivered by compression. Squeeze reality hard enough and it keeps showing you a deeper layer. What looks final at one scale is provisional at the next. The rock yields to the atom. The atom yields to the electron sea. The electron-based structure yields to neutron matter. Neutron matter may yield to something more exotic, and beyond that, the distinction between matter and geometry may yield to a theory we do not yet possess. Pressure keeps taking the visible world apart and asking whether you're sure this is the deepest level. The honest answer has had to remain no. That does not make the question futile, quite the opposite. It makes it one of the most revealing questions we can ask. Because every time matter answers the squeeze, it tells us what laws are governing the world at that scale. A material sample tells us about bonding and structure. A planet tells us about mineral phases and self-compression. A white dwarf tells us about electrons and quantum exclusion. A neutron star tells us about nuclear matter and strong gravity. The final threshold tells us something more difficult and more profound. It tells us that the current book of physics has pages missing precisely where matter is driven to its last meaningful limit. And maybe that is the right place to leave our attention for the moment. Not with a false certainty, and not with a dramatic collapse into pure mystery, but with a very clear shape of understanding. Matter can endure far more pressure than surface life would ever guess. It can survive by changing form again and again. It can surrender chemistry without surrendering existence. It can give up atoms and still remain. It can endure the death of stars and persist in dense remnants held up by quantum law. But there comes a point where the question stops being how much pressure this or that kind of matter can bear, and becomes what reality is made of when matter itself is no longer the deepest stable story. That is the last threshold. Not just the strongest squeeze, but the narrowest point at which the word matter still means enough to guide us. Beyond it lies the territory where a future theory must tell us whether matter dissolves into geometry, whether geometry dissolves into quantum structure, or whether both are shadows cast by something stranger and simpler than either one alone. And once you see the subject that way, pressure no longer feels like a mere mechanical quantity. It feels like one of the universe's most patient interrogators, steadily asking every layer of reality what it really is, and then leaning just a little harder until the next answer appears.